What if I told you that 95% of the entire universe is made of stuff we can't see, can't touch, and barely even understand? Every star you've ever admired on a clear night, every galaxy spiraling in the depths of space, they account for less than 5% of what's actually out there. The rest is an invisible realm of dark matter and dark energy, two cosmic mysteries that have puzzled astronomers and physicists for decades. We live in a universe where most of reality is hidden from us, a silent, shadowy ocean in which the visible cosmos is just a flicker of light on the surface. This profound unknown is what makes the study of our universe so endlessly fascinating. Even with our most powerful telescopes and sophisticated instruments, we're only beginning to scratch the surface of what's truly out there. From the strange behavior of galaxies to the accelerating expansion of the cosmos, the more we learn, the more we realize how much we still don't know. It's a humbling thought, one that invites curiosity, wonder, and a deep sense of awe at the scale and complexity of existence itself. In this video, we're going to explore 30 of the most intriguing cosmic phenomena that continue to challenge our understanding of space, time, and reality. These aren't just scientific curiosities, they're gateways to new ways of thinking, clues that might one day help us unravel the deepest secrets of the universe. So settle in, open your mind, and join us on this journey through the great unknown, where every discovery raises new questions and every mystery beckons us further into the cosmos. But the first mystery pulls us much closer to home, at least on a cosmic scale. Imagine you're floating in space, observing the Milky Way from the outside. You'd see our galaxy, along with our entire local group of galaxies, moving through the universe, but we're not drifting randomly, we're being pulled. Something with an unimaginable gravitational force is tugging on us, along with thousands of other galaxies, drawing us toward a specific point in the constellation Centaurus at a staggering speed of over 14 million miles per hour. This irresistible force is known as the Great Attractor. The intrigue deepens when we try to locate this cosmic heavyweight. It lies in a region of space astronomers called the zone of avoidance. This isn't a forbidden area of the universe, but rather a part of our sky that is obscured from our view by the dense disk of our own Milky Way galaxy. It's like trying to see a distant mountain range through a thick, perpetual fog bank of cosmic dust, gas, and stars. For the longest time, this visual blockade prevented us from getting a clear look at what was exerting such a powerful pull on us. So how do we know it's there if we can't see it? We detect its presence through the motion of galaxies themselves. By meticulously mapping the velocities of countless galaxies, astronomers noticed this consistent directional flow, a cosmic river of star systems all moving toward the same destination. The sheer scale of this motion points to a concentration of mass so enormous that it defies easy explanation. It's estimated that this gravitational anomaly must contain the mass of tens of thousands of Milky Ways. This isn't just a large galaxy or a cluster. It's a supercluster of galaxies, a node in the cosmic web of such immense proportions that its gravity dictates the motion of everything around it for hundreds of millions of light years. Modern technology is finally beginning to pierce through the obscuring veil. Space-based telescopes that observe in infrared and X-ray wavelengths, which can penetrate dust that blocks visible light, have started to map this hidden realm. What they've revealed is that the Great Attractor itself is likely part of an even larger structure, known as the Laniakea supercluster, of which our own local group is just a tiny suburb. This discovery reframed the mystery, showing us that the pull we feel is not from a single point, but from the collective gravitational draw of this vast cosmic continent. Yet the fundamental question remains, what exactly is at the very heart of this immense pull? While we now know it's a dense confluence of galaxy clusters, some scientists speculate there could be something even more unusual contributing to its incredible gravity. The Great Attractor stands as a profound reminder that even the grandest motions of our galaxy are governed by forces originating in the hidden depths of the cosmos, forces we are only just beginning to comprehend. While the Great Attractor reveals the influence of hidden mass on a colossal scale, it points us toward an even deeper and more pervasive cosmic secret. The gravity pulling entire superclusters of galaxies is not just coming from vast collections of visible stars. In fact, the stars themselves are only a small part of the story. This brings us to the second and perhaps most famous cosmic enigma, dark matter. Think about a child on a swing. The faster they go, the more force it takes to keep them moving in a circle, otherwise they'd fly right off. Now picture an entire galaxy like our Milky Way. Stars at the outer edge of the galaxy's disk are orbiting the center, held in place by the gravitational pull of all the mass inside their orbit. Based on the amount of light we see, all the stars, gas, and dust, we can calculate how fast those outer stars should be moving. The shock came in the 1970s when astronomer Vera Rubin measured the rotation speeds of these distant stars. She found they were moving far too quickly. According to the laws of gravity and the visible mass we can detect, those stars should have been flung off into the void long ago. The only possible explanation was that there had to be far more mass in the galaxy than we could see, mass that doesn't emit or interact with light in any way. This invisible mass, this gravitational glue holding galaxies together, is what we call dark matter. But how can we be so sure it's there if it's completely invisible? Another profound piece of evidence comes from a phenomenon predicted by Einstein's theory of general relativity: gravitational lensing. Massive objects warp the fabric of spacetime itself, bending the path of light that travels near them. This acts like a cosmic magnifying glass. When astronomers look at massive galaxy clusters, they sometimes see distant galaxies behind them stretched and distorted into faint arcs and rings. The amount of distortion reveals the total mass of the foreground cluster. Time and again, the mass required to create that extreme bending is vastly greater than the mass of all the visible stars and hot gas combined. It's as if we're looking at a mountain but only seeing the tip, while the rest of its immense bulk is hidden beneath the surface, revealed only by its profound effect on the landscape around it. So what is this mysterious substance? The leading theory suggests dark matter is made of particles that do not interact with the electromagnetic force, meaning they don't absorb, reflect, or emit light. They essentially ignore normal matter passing through our planet, our homes, and even our bodies as if we weren't even there. The prime candidates are known as weakly interacting massive particles, or WIMP. These hypothetical particles would have considerable mass compared to subatomic particles, but they'd only interact with normal matter through gravity and the weak nuclear force, making them incredibly difficult to detect. For decades, scientists have been conducting elaborate experiments deep underground in abandoned mines and tunnels, shielded from cosmic rays, hoping to catch the incredibly rare ping of a WIMP colliding with an atom in a specialized detector. So far, these elusive particles have managed to avoid capture. The ongoing failure to directly detect WIMP has led physicists to consider other possibilities. Could dark matter be made of something else entirely? Another candidate is the action, a particle that would be extremely light but exist in such vast numbers that it could account for the missing mass. There are even more exotic ideas, such as the theory that dark matter might be a property of gravity itself, requiring a modification of Einstein's equations on the largest scales. Each possibility opens a new door in our quest to understand the true composition of the universe, a quest that continues to challenge our most fundamental assumptions about reality. Yet for all its invisible power, dark matter is still a gravitational force, acting as the cosmic scaffolding that pulls the universe together. But what if I told you there is something else out there, an even more baffling and dominant force that is doing the exact opposite? It is not pulling the cosmos together, but actively and violently tearing it apart. This leads us to our third and perhaps most profound cosmic mystery, dark energy. The story of its discovery is one of the greatest plot twists in the history of science. For much of the 20th century, astronomers were locked in a debate about the ultimate fate of the universe. Would the collective gravity of all matter eventually slow its expansion from the Big Bang enough to cause a big crunch, pulling everything back into a single point? Or would the universe continue to expand forever, gradually cooling into a dark, frozen stillness? The prevailing assumption was that gravity, while weak over small distances, would act as a brake on the cosmic expansion over billions of years. To settle the debate, two independent teams of researchers in the late 1990s set out to measure the rate of this slowing down by studying incredibly distant stellar explosions known as Type 1a supernova. These supernovae are crucial because they all erupt with nearly the same intrinsic brightness, making them perfect standard candles for measuring vast cosmic distances. What these teams found, however, sent shockwaves through the world of physics. The data from these faraway supernovae revealed that they were much fainter, and therefore much farther away, than their redshifts indicated they should be if the universe's expansion was slowing down. The only possible explanation was that the expansion of the universe wasn't slowing down at all. It was speeding up. Some unknown repulsive force was working against gravity, pushing galaxies away from each other at an ever-increasing rate. This stunning revelation, which earned team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, meant that our understanding of the cosmos was fundamentally incomplete. This mysterious force driving the acceleration was christened dark energy. Today, measurements from the Planck satellite and other observatories suggest that dark energy makes up a staggering 68% of the total mass energy content of the universe, making it the single most dominant component of reality. Yet, we have almost no idea what it is. The leading hypothesis reaches back to an idea Albert Einstein himself once proposed and then discarded. He called it the cosmological constant, a property of empty space itself that exerts a negative pressure, causing spacetime to expand. In this view, the vacuum of space is not truly empty. It is seething with quantum fluctuations, a roiling foam of virtual particles that pop in and out of existence, and this energy might be the source of the repulsive force. However, this idea faces a monumental problem. When physicists try to calculate the predicted energy density of this quantum vacuum, the theoretical value is off from the observed value by a factor of 10 to the power of 120. This is arguably the worst prediction in the entire history of science, a number so impossibly large it indicates a deep and fundamental error in our understanding. This failure has led scientists to explore other, even more exotic possibilities. Perhaps dark energy is not a constant but a dynamic field that changes over time, a concept dubbed quintessence after the classical fifth element. This field could dilute or strengthen, potentially altering the ultimate fate of the universe in ways we cannot yet predict. The existence of dark energy challenges the very core of physics, suggesting that either our grasp of gravity is wrong on the largest scales, or that there is a completely new type of energy at work, one governed by laws we have yet to discover. It paints a startling picture of our cosmic future, one where the acceleration continues unchecked, eventually ripping apart galaxy clusters, solar systems, and perhaps even the fabric of spacetime itself in a distant event known as the Big Rip. Dark energy is the ultimate wild card, a force that confirms we are still only beginners in our quest to understand the true nature of the universe. Now, if dark energy is the force relentlessly pushing the cosmos apart on the grandest scale, our next mystery involves sudden, violent explosions of energy on a much smaller, but infinitely more intense scale. These are events so powerful and so brief that if you blinked you'd miss them, yet in that fraction of a second they can outshine 500 million suns. We are talking about fast radio bursts, or FRB. The story of their discovery begins not with a grand telescope but with archived data. In 2007, astronomer Duncan Lorimer and his student were reviewing observations from the Parkes Radio Telescope in Australia taken 6 years earlier. Buried in the recordings was a single, monumental spike of radio energy that lasted just 5 milliseconds. It was so intense and so isolated that for years, many in the scientific community were skeptical, wondering if it was some terrestrial glitch or a malfunctioning microwave oven on the observatory grounds. But then other telescopes began finding them too. These were not errors, they were real, they were cosmic, and they were utterly bewildering. What makes an FRB so extraordinary is its almost impossible intensity packed into an unimaginably short time. A typical burst might last only 1,000th of a second, but in that fleeting instant, it can release more energy than our sun puts out over 80 years. Because these bursts travel across millions or even billions of light years, their signals become stretched and scattered by the tenuous clouds of electrons scattered between galaxies. This actually gives astronomers a unique tool. By measuring how much the burst has been spread out, they can map the distribution of this missing ordinary matter, solving one mystery while investigating another. For a long time, every new FRB detected was a one-off event, a cosmic flash in the pan that appeared once and was never heard from again. This made them nearly impossible to pinpoint and study. The major breakthrough came in 2016 when the Arecibo telescope in Puerto Rico discovered something revolutionary, an FRB that repeated. It wasn't just a single blast, it would fire off multiple times, seemingly at random intervals. This proved that whatever was causing these explosions, at least some of them did not destroy their source in the process. This opened the door to truly studying them, as astronomers could now point other telescopes at the coordinates and wait for another burst to happen, hoping to catch it in the act across different wavelengths of light. So what cosmic engine could possibly create such a spectacular, fleeting blast? The repeating FRBs helped narrow the field of suspects dramatically. Many of them have been traced back to their host galaxies, often young, chaotic galaxies actively forming stars. The most compelling evidence to date points to magnetars, which are a specific, ferocious type of neutron star. A neutron star is the ultra-dense, collapsed core of a massive star after it goes supernova. A magnetar is that, but with a magnetic field, SO Chinese letter, so powerful it's 1,000 trillion times stronger than Earth's. It's thought that starquakes on the surface of a magnetar, sudden shifts in its crust under immense strain, could crackle with enough energy to launch these brilliant radio bursts across the universe. However, the single, non-repeating bursts might have a different, even more cataclysmic origin. One leading theory is the collision of two neutron stars. When these incredibly dense objects spiral into each other and merge, they are known to create powerful blasts of energy like gamma-ray bursts and gravitational waves. It's conceivable that such a monumental merger could also produce a one-time, colossal fast radio burst as a final farewell. But the random and fleeting nature of these events makes confirming this theory incredibly difficult. We have to be looking at exactly the right patch of sky at exactly the right millisecond. This inherent randomness is the greatest challenge in solving the FRB mystery. We cannot predict when or where the next one will appear. Astronomers must constantly monitor vast swaths of the sky, hoping their instruments are pointed in the right direction when one of these cosmic lightning strikes occurs. New telescopes like the CHIME Array in Canada are now doing just that, discovering thousands of these events and giving us a much larger sample to study. With each new detection, the plot thickens. Some bursts appear to be slightly polarized, a clue that they pass through powerful magnetic fields near their source. Others are astonishingly bright, suggesting something even more exotic than magnetars, perhaps involving black holes or speculative physics we haven't even dreamed of yet. But if the universe is capable of producing such brief, brilliant flashes of energy, it makes you wonder what else might be out there broadcasting. With hundreds of billions of stars in our galaxy alone, and many of those likely hosting planets in the habitable zone, the cosmos seems perfectly primed for life. This very line of thinking brings us to one of the most profound and haunting questions in all of science. Where is everybody? This is the essence of the Fermi Paradox. The story goes that in the summer of 1950, physicist Enrico Fermi was having a casual lunch conversation with colleagues at Los Alamos National Laboratory. The talk turned to flying saucers and the possibility of faster-than-light travel. As the story is told, Fermi suddenly blurted out, "But where is everybody?" His point was devastatingly simple. The universe is ancient, nearly 14 billion years old. Our galaxy is about 13 billion years old. Our solar system is a relative newcomer at 4.5 billion years old. That means there was a multi-billion-year head start for other civilizations to arise, develop technology far beyond our own, and eventually expand across the Milky Way. Even at a small fraction of the speed of light, such a civilization could colonize the entire galaxy in a few tens of millions of years, a mere blink of an eye on cosmic timescales. The fact that we see no obvious signs of these galactic empires, no massive engineering projects, and no visitors knocking on our door creates a startling contradiction. This paradox was later formalized by astronomer Frank Drake with his famous equation. It wasn't designed to give a single answer, but to frame the debate by breaking down the enormous question of extraterrestrial intelligence into more manageable variables. The Drake equation multiplies factors like the average rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops technology to communicate, and finally, the length of time such civilizations release detectable signals into space. Plug in optimistic numbers and you might get a galaxy teeming with thousands of communicative civilizations. Use more conservative estimates and the number could drop to a handful or even just us. The equation shows that the paradox isn't really a paradox of probability, but a paradox of observation. The math suggests they should be there, but our telescopes remain silent. This silence has led to a deeply unsettling idea known as the Great Filter. This theory suggests that there is some kind of barrier, a nearly insurmountable challenge that prevents life from progressing to the stage of interstellar colonization. The terrifying question is where this filter lies. Is it behind us? Perhaps the emergence of life itself is an astronomically rare fluke, or maybe the jump from simple prokaryotic cells to complex eukaryotic life was a 1 in a billion event. If so, we are impossibly lucky, but we are also utterly alone. The more frightening possibility is that the Great Filter is ahead of us. It could be that almost all advanced civilizations inevitably destroy themselves upon discovering certain technologies, whether through nuclear war, runaway climate change, engineered pandemics, or a future technology we haven't even conceived of yet. In this scenario, the cosmic silence is a warning, a graveyard of species who failed to overcome their own self-destructive tendencies. Scientists and thinkers have proposed a zoo of other potential solutions, some comforting, others deeply strange. The zoo hypothesis suggests that advanced civilizations are out there and aware of us, but they are deliberately avoiding contact, perhaps to allow us to develop naturally like animals in a cosmic preserve. The planetarium hypothesis is even more mind-bending. It posits that our entire observed universe could be an elaborate simulation or a projection created by a superior intelligence, meaning the emptiness we see is just a facade. Other ideas are more practical. Perhaps interstellar travel is simply too difficult or too expensive for anyone to bother with. Maybe civilizations don't last long enough to make the journey, or they transcend biological form into something we can't recognize or detect, like a collective consciousness or beings of pure energy. It's possible they use a communication technology so advanced that it's completely invisible to our primitive radio telescopes, just as Wi-Fi would be magic to someone from the 19th century. At its heart, the Fermi Paradox holds up a mirror to humanity. In searching for others, we are ultimately forced to confront our own future. Are we on the cusp of passing through a filter that has doomed every other species, or are we just the first to arrive at the party, destined to be the ancient ones that future civilizations will wonder about? The search continues with projects like SETI scanning the skies for any artificial signal. Every time we look up at a silent, star-filled night, we are confronted with the profound weight of that question. The silence is not empty, it is full of possibilities, each one telling a different story about life, the universe, and our place within it. While the Fermi Paradox confronts us with a profound and unsettling cosmic silence, there was one brief moment where that silence was broken, a signal so unusual and so perfectly aligned with what we might expect from an artificial broadcast that it etched itself into history as perhaps the most famous blip in the search for extraterrestrial intelligence. This is the story of the WOW signal. It all began on a quiet August evening in 1977. Ohio State University's Big Ear radio telescope was dutifully scanning the sky, part of the long-running SETI project searching for narrowband radio signals that could indicate a technological source. Most of the data was unremarkable, just the constant hiss of cosmic static, but on August 15th at 10:16 p.m., the computer printout told a different story. The signal was intense, occupying a single, very narrow frequency band centered on 1420 MHz. This frequency is significant because it lies within a protected band of the spectrum known as the water hole, where radio waves travel through the cosmos with minimal interference from natural sources, a logical place for a civilization to broadcast. The signal also exhibited a telltale rise and fall in intensity over exactly 72 seconds, precisely matching what you would expect as the Earth rotation carried the stationary telescope's field of view across a fixed point in the sky. It was a perfect match for an extraterrestrial beacon. The data was printed on continuous feed paper, and a few days later, volunteer astronomer Jerry Amon was reviewing the readouts. Stunned by the signal's strength and its perfect characteristics, he circled the alphanumeric sequence, 6-5, which represented the signal's intensity, and scribbled, "Wow." In the margin, the name and the mystery stuck. The signal was 1 billion times stronger than the background cosmic noise. It was not a repeated military transmission or a passing airplane. It came from deep space, specifically from a region in the constellation Sagittarius near the star group Chi Sagittarii. It had all the fingerprints of an intelligent, deliberate broadcast. The immediate and obvious next step was to try and hear it again. If an alien civilization was out there sending a greeting, surely they wouldn't transmit it just once. The Big Ear telescope and countless others since have pointed back at that same spot in the sky hundreds of times over the decades, listening intently for a repeat performance. The result has been a deafening and perplexing silence. Nothing even remotely like the WOW signal has ever been detected from that location again. This failure to find a repeat is the single biggest argument against an extraterrestrial intelligence origin. Why would they broadcast just once? This enduring puzzle has fueled a relentless search for a natural explanation. Could it have been a signal reflected off a piece of space debris, like a discarded rocket booster? The frequency doesn't match any known human transmissions from that era, and the reflected signal theory generally produces a much wider, messier burst. Another idea points to a cometary hydrogen cloud. In 2017, an astronomer proposed that two comets, which happened to be passing through that region of sky in 1977, could have been surrounded by vast clouds of hydrogen gas. The Big Ear telescope was tuned to the frequency at which hydrogen naturally emits radio waves. Perhaps the signal was just this natural emission, amplified by the comet's movement. This was a compelling idea, but it ultimately fell apart under scrutiny. The comets were not actually in the exact part of the sky the signal came from when it was detected, and subsequent analysis showed that the hydrogen emission from such comets would be far too weak to account for the incredibly powerful WOW signal. So where does that leave us? The natural explanations proposed so far have all been found wanting, unable to fully account for the signal's unique and powerful properties. Yet the lack of a repeat performance makes the alien hypothesis equally difficult to prove. It remains in a tantalizing limbo, the ultimate celestial one-hit wonder. Its power and precision keep it at the forefront of SETI lore because it represents a glimpse of what a true detection might look like. It was a signal that passed every initial test for artificiality we could throw at it. The WOW signal endures not as an answer but as a promise. It is a reminder that the cosmos might indeed be speaking. We just happen to be listening to the right channel at the right moment for 72 glorious seconds. The challenge is to keep listening in the hope that one day the silence will break again, and this time it will say more than just wow. From the fleeting brilliance of fast radio bursts to the haunting silence of the Fermi Paradox, our search for cosmic company often feels like grasping at shadows. But what if we found a shadow so bizarre, so utterly colossal, that the most rational explanation seemed to be the work of an intelligence beyond our own? This isn't science fiction, it's the very real and deeply perplexing mystery of Tabby's star, officially catalogued as KIC 8462852, but forever known by the name of its principal investigator, Tabitha Boyajian. This star first shot to fame in 2015. It was discovered in data from NASA's Kepler Space Telescope, a mission designed to find planets by watching for the tiny, periodic dips in starlight they cause as they transit or pass in front of their host star. Typically, a planet like Jupiter might block about 1% of a sun-like star's light, but the data from Tabby's star was anything but typical. Kepler recorded dips in its brightness that were staggering, some as deep as 22%. That's not a planet, that's an object nearly a quarter the size of the star itself passing in front of it. Even more strangely, these dimming events were completely irregular. There was no predictable pattern, no set timetable. They would happen for days or weeks at a time, with the star's brightness sometimes changing dramatically from one hour to the next, a level of volatility that is utterly unprecedented for a star of its type. The immediate and most tantalizing theory to emerge was the possibility of alien megastructures. Specifically, scientists and the public alike latched onto the concept of a Dyson sphere, a hypothetical shell of solar collectors built by an advanced civilization to harness the entire energy output of its star. A partially constructed or swarm-like Dyson sphere could, in theory, explain the massive, irregular blocks of light we were seeing. It was a hypothesis that captured the global imagination, turning a faint star over 1,000 light-years away in the constellation Cygnus into an international sensation. Of course, astronomers are a methodical bunch, and they began rigorously testing more natural, albeit still exotic, explanations. The leading contender for years has been a giant, swarming family of comets. The idea is that a vast cloud of cometary fragments, surrounded by immense clouds of dust and gas, could be on a long, eccentric orbit around the star. As they break up and disperse, they could create the very kind of deep, irregular dimming we observe. It's a plausible scenario, but it has its own problems. To create dips that big, you'd need an almost unimaginable number of comets, far more than we see in our own solar system, making it a rather extraordinary claim in its own right. Other theories have poured in. Perhaps the star recently devoured a planet, creating a temporary disk of debris that is now causing these strange shadows. Maybe there's a giant planet with enormous, dusty rings like Saturn on steroids that are tilting at different angles as it orbits, or the answer could lie not in front of the star but with the star itself. Could it be going through a unique and volatile phase in its life, causing immense star spots or internal pulsations that affect its brightness. Detailed observations of the star's light spectrum have largely ruled out this last idea. The dimming is almost certainly caused by something solid passing in front of it, as different colors of light are blocked equally, pointing to an opaque object rather than an internal process. The real intrigue deepened when astronomers delved into historical data. By examining old photographic plates of the sky from the late 19th century, they found that Tabby's star appears to have been gradually dimming over the entire past century by a significant amount. This long-term dimming, combined with the short-term drastic dips, makes the mystery even harder to unravel, as it suggests there are multiple, overlapping phenomena at work around this one strange star. So where does the investigation stand today? The alien megastructure hypothesis, while never the favorite among scientists, has become increasingly difficult to sustain. In-depth studies using the Los Cumbres Observatory Global Telescope Network have shown that the dimming affects different colors of light in a way that is perfectly consistent with ordinary dust. Fine particles tend to scatter blue light more than red light, so a dusty object would cause a star to appear slightly redder as it dims. That's exactly what we see with Tabby's star. A solid, metallic megastructure, by contrast, would likely cause a more uniform dimming across all colors. The dust discovery doesn't solve the mystery, it just reframes it. We're now searching for the source of this incredible amount of dust. What catastrophic event could have created such a massive, complex, and dynamic cloud of debris? The answer remains just out of reach, a testament to the fact that the universe is still full of surprises that defy our immediate understanding. Tabby's star endures not as proof of aliens, but as proof that nature still has a few tricks up its sleeve, capable of producing wonders strange enough to fuel our wildest dreams. While mysteries like Tabby's star invite us to look outward at distant suns, some of the most perplexing cosmic puzzles have been discovered much closer to home, hiding in plain sight within our own solar system. This brings us to a decades-long enigma that played out not with telescopes, but with the subtle, unexpected behavior of two of humanity's most intrepid explorers, the Pioneer 10 and 11 spacecraft. Launched in the early 1970s, Pioneer 10 and 11 were true trailblazers. Pioneer 10 was the first spacecraft to travel through the asteroid belt and the first to make direct observations of Jupiter, while Pioneer 11 went on to capture the first close-up images of Saturn. After completing their primary missions, both spacecraft continued on trajectories that would eventually carry them out of the solar system entirely, becoming silent ambassadors drifting into the interstellar void. But as they journeyed farther from the Sun, deep into the cold, dark realm beyond the orbit of Uranus, NASA navigators began to notice something peculiar. Both spacecraft were experiencing a tiny, unexplained deceleration. It was as if an invisible hand was ever so gently applying the brakes, pulling them back toward the inner solar system. This deviation was minuscule, roughly 300 billionths of a meter per second squared, a force comparable to the weight of a single grain of sand pressing on your hand. But in the precise world of orbital mechanics, where calculations are measured down to the atomic scale, this anomaly was massive and undeniable. For nearly 30 years, this pioneer anomaly defied all conventional explanation. Could it be the gravitational pull of an unknown, undiscovered planet lurking in the dark? The effect was consistent and identical for both probes, which were traveling in nearly opposite directions, effectively ruling out a single, localized source like a planet. Perhaps it was a subtle drag from interstellar dust or gas. The density of matter out there is far too low to produce any measurable effect. The most tantalizing and controversial hypothesis was that we were seeing the first hint of a flaw in our understanding of gravity itself. Maybe Einstein's theory of general relativity needed a slight modification over extremely large distances, a new physics that would reveal itself only in the deepest reaches of space. The resolution to this mystery is a masterclass in scientific detective work and a lesson in humility. The culprit, it turns out, was not a hidden planet or a revolution in physics, but something far more mundane: heat. The Pioneer probes were powered by radioisotope thermoelectric generators, which produced electricity from the natural decay of plutonium. This process also generated a significant amount of waste heat. The spacecraft were designed with a main antenna always pointed back toward Earth, which meant this heat was radiated away preferentially from the back of the craft. Every photon of that infrared radiation pushing off the antenna dish acted like a tiny, gentle photon rocket thruster. The net effect was a minuscule but constant pressure pushing against the direction of travel, exactly the anomalous deceleration the navigators had measured. Meticulous computer modeling and analysis of decades of telemetry data eventually confirmed that this thermal radiation pressure accounted for the vast majority of the mysterious force. Yet, even with this elegant solution, a whisper of the anomaly remains. While thermal radiation explains most of the effect, some analyses suggest there might be a tiny sliver of the deceleration, a few percent, that is still unaccounted for. This leftover discrepancy lies in the uncomfortable realm of measurement uncertainty. It could be the result of unmodeled gas leaks from the spacecraft's thrusters, or perhaps an incomplete understanding of how the heat was actually distributed across the complex surfaces of the probes. It serves as a permanent reminder that at the very edge of our measurement capabilities, there will always be a faint signal of the unknown. The legacy of the Pioneer anomaly is profound. It teaches us that the universe often reveals its secrets not in grand, obvious gestures, but in the faintest of whispers, detectable only through painstaking, precise observation over decades. It's a story that underscores the incredible precision required for deep space navigation and the importance of accounting for every conceivable variable, no matter how small. Most importantly, it demonstrates the self-correcting nature of science. A mystery that once threatened to upend our understanding of gravity was ultimately solved by a thorough and relentless examination of the data, a testament to the power of curiosity and perseverance in the face of the unknown. If the Pioneer anomaly taught us to look for answers in the subtle physics of our own spacecraft, our next mystery forces us to question the very foundation of modern cosmology itself, and it all begins with the oldest light we can see. This is the story of the cosmic microwave background, or CMB, and a baffling alignment within it that cosmologists have grimly nicknamed the axis of evil. To understand why this is so unsettling, we need to rewind to the beginning. The CMB is the faint afterglow of the Big Bang, the cooled remnant of the universe's fiery birth nearly 14 billion years ago. It fills the entire sky, a snapshot of the universe when it was just a mere 380,000 years old, a searing plasma of particles and energy that finally cooled enough for light to travel freely for the first time. This radiation is not perfectly uniform. It's imprinted with tiny temperature fluctuations, anisotropies that represent the seeds of all future structure. The slight over densities that would one day gravitationally collapse into the vast cosmic web of galaxies and galaxy clusters we see today. According to our standard model of cosmology, these fluctuations should be completely random, with no preferred direction or alignment. The universe, on its largest scales, is supposed to be isotropic and homogeneous, meaning it looks the same in every direction and from every location. This is the cosmological principle, the bedrock assumption upon which almost all of modern cosmology is built. This is where the plot thickens. In 2003, and then with even greater precision from NASA, a Wilkinson microwave anisotropy probe, scientists created a full sky map of these CMB temperature variations. When they analyzed this map, they found something that should not exist. The fluctuations weren't entirely random. They displayed a strange, unexpected alignment with the plane of our own solar system. This peculiar correlation, this apparent preferred direction in the cosmos, is what earned the dramatic moniker, the axis of evil. The name, coined by cosmologist Joe Megiddo, is intentionally provocative, reflecting just how threatening this observation is to our standard models. It suggests that the solar system's ecliptic plane, a purely local and insignificant structure on a cosmic scale, is somehow mysteriously linked to the larger scale features of the entire observable universe. It's as if the wallpaper in your house was somehow perfectly aligned with the street pattern of your entire city. The two should have absolutely nothing to do with each other. So what could possibly be causing this? The most worrying possibility is that it's not a real cosmological effect at all, but a systematic error or a contaminant in our data. Perhaps our own galaxy is getting in the way. Dust and gas in the Milky Way emit microwaves that could potentially be skewing the measurements. Teams have worked tirelessly to subtract this foreground contamination, and while it accounts for some anomalies, the axis of evil signal stubbornly persists. Another, more unsettling thought is that it's a psychological artifact, a form of cosmic pareidolia where we're unconsciously imposing a pattern where none exists. But the statistical significance of the alignment has held up under intense scrutiny, making this seem increasingly unlikely. The signal, as faint as it is, appears to be real. This forces cosmologists to consider truly paradigm-shifting ideas. Could the cosmological principle be wrong? Is the universe not the same in all directions? Perhaps the universe has a large-scale structure or rotation we are not aware of, an inherent anisotropy that gives it a preferred axis. Some theories even suggest our universe might have collided with another universe in the multiverse during its inflationary phase, imprinting a directional preference on the fabric of spacetime. These are not ideas proposed lightly. They are last resorts invoked only because the standard model has so far failed to explain this bizarre observation. Yet, the most humbling explanation of all is one of perspective. The axis of evil might be the ultimate reminder of our own cosmic mediocrity. We are not privileged observers. The alignment we see might simply be a colossal coincidence, a random fluke that happens to look significant from our particular vantage point in the universe. In an infinite or vastly large cosmos, even the most improbable patterns are bound to appear somewhere. The challenge is determining whether we are that somewhere, or if the universe is genuinely trying to tell us something profound about its true nature. The axis of evil remains one of the most significant unsolved problems in cosmology, a quiet but persistent whisper in the static of the Big Bang that suggests our map of the universe is still missing some fundamental and perhaps terrifying features. But if the axis of evil challenges our view of the universe's largest scales, our next mystery forces us to confront the very fabric of reality itself on the smallest scales imaginable. This phenomenon is so bizarre, so counterintuitive, that it famously troubled even Albert Einstein, who dubbed it spooky action at a distance. We are talking about the mind-bending world of quantum entanglement. Imagine you have a pair of magical dice. You take them to opposite ends of the galaxy, ensuring they are completely isolated from each other. You roll one die on your end and it comes up a 4. Instantly, at that exact moment, the die on the other side of the galaxy also shows a 4. This isn't just a coincidence, it's a fundamental link. This, in essence, is what happens with entangled particles. They are born together, their properties become deeply intertwined, and no matter how far apart they are separated, they remain a single, connected quantum system. Measure one, and you instantly know the state of its partner. Change one, and its partner seems to respond immediately. This idea so violated our classical intuition about how the universe should work that Einstein, along with colleagues Boris Podolsky and Nathan Rosen, proposed it as a paradox in 1935 to argue that quantum mechanics must be an incomplete theory. Their reasoning, now called the Fermi Paradox, was rooted in two seemingly unshakable principles. The first is locality. the idea that objects can only be influenced by their immediate surroundings and that no signal or information can travel faster than the speed of light. The second is realism, the assumption that particles have definite, pre-existing properties waiting to be measured, like a coin that is either heads or tails even before you look at it. Entanglement, with its suggestion of instantaneous connection across any distance, appeared to smash both these principles to bits. Einstein believed there must be some deeper, hidden variables at play that quantum theory hadn't yet accounted for, which would restore a sensible local reality. For decades, this remained a fascinating philosophical debate. Then, in the 1960s, a brilliant physicist named John Bell found a way to test it. He devised a mathematical theorem, Bell's theorem, that provided a concrete experimental way to distinguish between Einstein's local hidden variables and the spooky, non-local world of standard quantum mechanics. The experiments are intricate, but the essence is this: if local hidden variables are real, then the correlation between measurements on entangled particles cannot exceed a certain limit. Quantum mechanics, however, predicts a stronger correlation, one that violates this limit, beginning in the 1970s and continuing with ever-increasing precision to this day. Physicists have performed these tests. They've used entangled photons, electrons, and even entire atoms, separating them by meters, then kilometers, and now by hundreds of kilometers using fiber optic cables and even satellites. The results are unequivocal. Again and again, quantum mechanics wins. The particles violate Bell's inequality, demonstrating that their connection is real and that no local hidden variable theory can explain their behavior. The universe, on its most fundamental level, is non-local. What happens to one particle truly does affect its entangled partner instantly, regardless of the distance between them. But before you imagine this as a way to send faster-than-light messages, there's a crucial catch. This instantaneous change may be real, but it cannot be used to transmit information. The outcome of measuring your entangled particle is always random. You only know what your partner measured after the fact by comparing notes through a conventional, slower-than-light communication channel. It's like opening one of two boxes to find either a black or white glove. The instant you open your box and see a black glove, you know the other box contains a white one. But you didn't cause the other glove to be white. That outcome was set the moment the gloves were placed in the boxes. The spookiness is in the correlation, not in controllable communication. This bizarre behavior forces us to radically rethink the nature of reality. It suggests that at its core, the universe may not be made of separate, independent things, but is rather a deeply interconnected whole. The properties we assign to particles, like spin or polarization, may not exist as definite values until the moment they are measured, a concept that erodes the very idea of an objective reality independent of observation. Some interpretations, like the Copenhagen interpretation, embrace this, stating that the wave function only collapses upon measurement. Others, like the many worlds interpretation, propose that every quantum possibility is realized in a branching multiverse. And then there is pilot wave theory, which posits that particles do have definite positions, guided by a non-local wave, but this requires accepting that influence can indeed travel faster than light. The implications of entanglement stretch far beyond philosophical puzzles. They are the foundation of a technological revolution. This quantum link is the core principle behind quantum computing, where entangled qubits can perform complex calculations in parallel that would take classical computers millennia. It is the heart of quantum cryptography, specifically quantum key distribution, where any attempt to eavesdrop on a communication instantly disrupts the delicate entangled state, alerting the users to the presence of an intruder and creating theoretically unhackable communication networks. Perhaps most profoundly, physicists are exploring whether this spooky connection could hold the key to one of the greatest unsolved problems in physics, unifying general relativity with quantum mechanics to find a theory of quantum gravity. The fabric of spacetime itself may emerge from a vast cosmic web of entangled quantum particles. In this view, the connectivity between distant points in space isn't a given. It is created and maintained by quantum entanglement. Where there is entanglement, there is a shortest path, a thread of spacetime. Where there is no entanglement, space itself may not exist in any meaningful way. This means that the strange, non-local ghostliness of the quantum world might not be a bug in our universe, but the very feature that stitches together the reality we experience, connecting the smallest particles to the largest structures in the cosmos in one seamless, incredible whole. Yet for all its strange interconnectedness, quantum entanglement operates within the well-established rules of quantum mechanics. It suggests that information, the fundamental data that describes every particle's state, is always preserved. You can scramble an egg, but in principle, if you could track every single quantum interaction, you could unscramble it. This principle of unitarity is a bedrock of quantum physics. But this unshakable rule runs headlong into one of the most terrifying and powerful objects in the universe, creating a paradox so deep that it has divided physicists for half a century. This is the black hole information paradox, and it begins with one of Stephen Hawking's most brilliant and troubling discoveries. We often think of black holes as the ultimate cosmic vacuums, sucking in everything that crosses their event horizon, never to be seen again. Hawking's revolutionary work in the 1970s showed that this isn't entirely true. He realized that by applying quantum theory to the very edge of a black hole, the point of no return, a miraculous escape becomes possible. The vacuum of space is not truly empty. It is a seething quantum foam where pairs of virtual particles constantly blink in and out of existence, borrowing energy from the universe before annihilating each other and paying it back in an incredibly short time. Hawking proposed that if this particle-antiparticle pair pops into existence right at the event horizon, one particle could fall in while the other escapes, stealing a tiny amount of the black hole's mass in the process. To an outside observer, the black hole isn't completely black. It is emitting a faint glow of radiation, now known as Hawking radiation. This radiation, however, presents a monumental problem. It is purely thermal, like the heat from a stove. It contains no information about the individual particles that made up the star, the spaceship, or the book that fell in. It only tells you the black hole's mass, charge, and spin. As the black hole radiates, it slowly loses mass and eventually evaporates completely in a final burst of energy. And if that final burst is also purely thermal, then all the detailed quantum information about everything that ever fell into the black hole has been irretrievably destroyed. This violates the core quantum mechanical principle that information cannot be created or destroyed, only transformed. It's the equivalent of burning a library and claiming the smoke and ash contain the same information as all the books. According to quantum law, this is impossible. We are left with a nightmarish choice. Either Hawking's calculation is wrong or quantum mechanics is fundamentally incomplete. This paradox pits two pillars of modern physics against each other. General relativity, which describes black holes, insists that the event horizon is uneventful. An object passing through it would notice nothing special, a concept called no drama. Quantum mechanics, with its demand for information conservation, insists that the destruction of information is unacceptable. For decades, physicists have proposed wild and ingenious solutions to resolve this conflict. One of the most prominent ideas is the holographic principle. It suggests that all the information describing the three-dimensional volume of a black hole is actually encoded on its two-dimensional event horizon, like a cosmic DVD. The information never actually falls in. It is smeared and stored on the surface. When Hawking radiation is emitted, it slowly and chaotically carries that information back out, encoded in subtle correlations between the radiation particles. The information isn't lost, it's just incredibly scrambled, like a message put through the world's most complex shredder. If you could collect all the radiation over the black hole's entire multi-billion-year lifespan, you could, in theory, reconstruct everything that ever fell in. An even more radical solution is the firewall hypothesis. Proposed in 2012, it suggests that to preserve information, the no-drama principle must be sacrificed. Instead of a smooth entry through the event horizon, an infalling astronaut would immediately be incinerated by a wall of ultra-high-energy radiation, a firewall. This violent boundary would prevent any information from crossing inside, thus resolving the paradox by ensuring information never actually enters a region where it could be destroyed. While mathematically possible, many physicists find this idea deeply unsatisfying, as it fundamentally alters our understanding of a black hole's edge based on who is observing it. Other theories propose that black holes don't evaporate completely but leave behind a tiny, information-packed remnant, a frozen fossil of all they have consumed. The problem here is that such an object would have to store an infinite amount of information in an infinitesimally small space, creating its own set of physical impossibilities. The debate rages on, with each potential solution curing one ill while creating another. The true resolution likely lies in a theory of quantum gravity, a unified framework that can describe the intense gravity of a black hole and the weirdness of the quantum world simultaneously. Until we have that final theory, the black hole information paradox remains a glaring signpost pointing toward a deeper layer of reality we have yet to uncover, where our current laws of physics meet their limits and something new must take over. This growing discrepancy in our cosmic speedometer is not a minor calibration error. It's a fundamental crisis that has come to be known as the Hubble tension. At its heart, the tension is a conflict between two impeccably reliable ways of measuring the universe's expansion. The first method looks back to the universe's infancy. By studying the exquisite details of the cosmic microwave background with satellites like Planck, cosmologists can see the imprint of the early universe's density waves. They then use our well-tested standard model of cosmology, lambda CDM, to run the clock forward and predict what the expansion rate should be today. This method provides an answer of approximately 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, which is about 3.2 million light-years, the universe expands 67 kilometers per second faster. The second method builds the cosmic distance ladder rung by rung to measure the expansion rate directly in our modern universe. Astronomers use pulsating stars called Cepheid variables and cataclysmic stellar explosions known as Type 1a supernova as standard candles. Because we know their intrinsic brightness, we can calculate their distance. By then measuring the redshift of their host galaxies, we can see how fast they are receding from us. This painstaking step-by-step process, championed by teams like the one led by Nobel laureate Adam Rees, yields a consistently higher and more precise value, around 73 kilometers per second per megaparsec. On the surface, a difference of a few kilometers per second might not seem like much, but the statistical significance is overwhelming. These are not error bars that overlap. They are two distinct answers separated by a chasm that grows with every new, more precise measurement. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two undeniably different results. The unsettling implication is that one of our rulers might be wrong, or worse, our understanding of the table itself is fundamentally flawed. This has sent cosmologists on a frantic hunt for explanations, which generally fall into two camps. The first possibility is that there are hidden systematic errors in our measurements. Perhaps our understanding of Cepheid variables is incomplete, or interstellar dust is subtly dimming our standard candles and skewing the local measurements. Yet, as teams have eliminated potential errors and employed new methods like using red giant stars at their peak brightness or the geometry of merging neutron stars, the higher local value has stubbornly held its ground, making a simple measurement error seem increasingly unlikely. This forces us to consider the far more exciting possibility that the Hubble tension is a sign of new physics. Our standard model of cosmology, for all its success, might be an incomplete picture of reality. Perhaps dark energy is not a constant but an evolving force that has changed strength over the history of the universe, throwing off the prediction from the early cosmos. There could be previously unknown types of dark radiation or exotic subatomic particles from the early universe that influenced its expansion history in a way our models don't account for. Some theorists have even revisited the idea of primordial magnetic fields or early dark energy, a transient field that altered the universe's expansion rate just before the formation of the cosmic microwave background. Resolving the Hubble tension is now one of the most pressing goals in modern cosmology. New observatories like the James Webb Space Telescope are being tasked with scrutinizing the cosmic distance ladder with unprecedented sharpness, hunting for any hidden flaws in our local measurements. At the same time, next-generation telescopes will map the large-scale structure of the universe with immense precision, offering a third, independent way to measure the expansion rate. The hope is that this crisis will not break our model of the cosmos, but break it open, leading us to a deeper, more complete understanding of the forces that have shaped our universe from its first moment to the present day. While black holes and the expansion of the universe present puzzles on the grandest scales, our next mystery arrives from the depths of space in the form of tiny, insanely energetic projectiles. These aren't just any particles, they are cosmic rays, atomic nuclei stripped of their electrons and accelerated to nearly the speed of light. Most originate from our sun or from violent events within our galaxy, like supernova explosions. But a few rare particles have been detected that defy all known physics, carrying so much energy that their very existence seems almost impossible. They are the ultimate cosmic bullets, and their origin is one of the most enduring puzzles in astrophysics. The champion of these ultra-high-energy cosmic rays was detected on the evening of October 15, 1991, by the Fly's Eye cosmic ray detector in the Utah desert. It was a single subatomic particle, most likely a proton, but it carried a kinetic energy of about 300 exa-electronvolts. To put that almost incomprehensible number into perspective, that single proton was moving with the energy of a baseball pitched at 60 miles per hour. Think about that for a moment. All the energy a professional pitcher puts into a baseball, packed into one infinitesimally small particle smaller than an atom. It was traveling at 99.9999999999996% of the speed of light, so close to the universal speed limit that in a race against a photon of light, it would only lose by less than a fraction of a centimeter over 100,000 light-years. The researchers who discovered it were so astounded that they dubbed it the "Oh my God" particle. This detection was not a fluke. Other observatories, like the Telescope Array Project in Utah and the Pierre Auger Observatory in Argentina, have since detected a handful of other particles with similarly monstrous energies. The existence of these particles creates a monumental problem for physicists. We simply don't know of any natural particle accelerator in the universe powerful enough to give a single proton that much of a kick. The primary challenge is something known as the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. This isn't a limit on the particles themselves, but a limit imposed by the universe. Space is not a perfect vacuum. It is filled with the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang. For a proton traveling at these ultra-relativistic speeds, that faint background light looks like a dense fog of high-energy photons. A proton from a distant source trying to reach Earth would inevitably collide with these photons long before it got here. It would be like trying to sprint through a downpour without getting wet. The proton would lose energy with each collision until its energy dropped below the GZK cutoff. This means that any oh my god particle we detect must have originated from within our local cosmic neighborhood, within a radius of about 160 million light-years. Its source must be relatively close by, and that's the heart of the mystery. Within that volume of space, we have a pretty good catalog of potential cosmic accelerators. We see supernova remnants, pulsars, and even the supermassive black hole at the center of our own galaxy. But none of them are remotely powerful enough to produce such a particle. The magnetic fields in these objects are simply not strong enough to confine a proton and accelerate it to such an extreme energy without it escaping. It would be like trying to accelerate a bullet to orbital velocity using a slingshot. The mechanism just can't contain that much force, so what cosmic engine is capable of this feat? Theorists have been forced to propose some truly exotic candidates. One leading idea involves active galactic nuclei, the incredibly luminous cores of galaxies powered by supermassive black holes that are actively feeding on matter. As material spirals into the black hole, it can create powerful jets of plasma shooting out from the poles at relativistic speeds. Perhaps magnetic fields within these jets can act as a natural synchrotron, accelerating particles to energies that dwarf anything we can create in our largest particle colliders. Another possibility is that the sources are gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. The catastrophic collapse of a massive star into a black hole or the merger of two neutron stars could unleash a short-lived but unbelievably powerful shockwave that could launch these particles. Some theories venture even further into the unknown. Could these particles be the signature of decaying super-heavy dark matter? If dark matter is made of hypothetical particles that were created in the early universe with immense mass, their decay products could include protons with the enormous energies we observe. This would be a two-for-one solution, potentially explaining both the origin of cosmic rays and the nature of dark matter itself. Other, more speculative ideas include cosmic strings, topological defects in the fabric of space-time left over from the early universe, or even the violent interactions of magnetic monopoles, hypothetical particles with a single magnetic pole. The hunt to solve this mystery is ongoing, and it relies on a detective technique as clever as it is necessary. Because these ultra-high-energy cosmic rays are so rare, catching them directly is incredibly difficult. Instead, giant observatories like the Pierre-Auger array don't try to catch the primary particle itself. They wait for it to strike the nucleus of an atom in the upper atmosphere. This collision creates a spectacular cascade of secondary particles, an expanding shower that rains down upon the Earth's surface. By deploying thousands of detectors over an area the size of Rhode Island, scientists can measure the footprint of this shower when it arrives. By analyzing its size, shape, and timing, they can work backwards to calculate the energy and the incoming direction of the original primary particle that started it all. This is how we are slowly beginning to map the sources of these incredible projectiles. Recent data from the Pierre-Auger Observatory has intriguingly suggested that the very highest energy cosmic rays may not be arriving evenly from all directions. Instead, they appear to be correlated with the locations of galaxies with active supermassive black holes beyond our local group, but still within the GZK limit. This is a tantalizing clue, but the statistics are still too low to declare the case closed. Each new detection is a precious piece of evidence, a message from one of the most powerful engines in the cosmos, and we are only just learning how to read it. Yet for all its violent and dramatic origins, our own moon presents a mystery that hits much closer to home. How did Earth acquire such a large, seemingly improbable companion? The answer is written in the moon's very rocks, and it tells a story of a cataclysm so immense it defined the earliest chapter of our planet's history. For centuries, astronomers proposed a host of elegant theories. Perhaps the moon was a wanderer, a rogue planet captured by Earth's gravity in a celestial game of catch. This is the capture theory. Or maybe the two bodies formed side by side from the same primordial cloud of dust and gas, a peaceful co-formation that would make them siblings. There was even the fission idea, suggesting that the early, rapidly spinning Earth bulged so much at its equator that it flung off a blob of material that became the Moon. But when Apollo astronauts brought back hundreds of pounds of lunar rocks, each of these elegant theories crumbled under the weight of the chemical evidence. The rocks revealed a shocking similarity. The isotopes of oxygen in the Moon's rocks, the unique fingerprints of an object's formation, were virtually identical to those found on Earth. This was a devastating blow to the capture and co-formation ideas. If the Moon had formed independently, even near Earth, it should have a distinctly different isotopic signature, just as Mars or an asteroid does. The fission theory seemed to gain some traction as it would explain the similarity, but it had its own fatal flaw: physics. The Earth simply never spun fast enough to throw off such a massive piece of itself, and even if it could, the Moon should have ended up orbiting over Earth's equator, not at the slight tilt we observe today. This left scientists with a puzzle. The Moon and Earth are isotopic twins, suggesting a common origin. Yet the Moon is significantly less dense than Earth, meaning it lacks a substantial iron core like our planets. It's as if you took the Earth, stripped away its metallic heart, and were left with a rocky mantle. How do you get an object made almost entirely of mantle material from one planet to form an entirely new world? The only scenario that could explain this bizarre combination of similarity and difference was something both brutal and incredibly precise: a giant impact. The giant impact hypothesis, often poetically called the Big Splash, is the leading theory today. It proposes that in the chaotic early solar system over 4.5 billion years ago, a young, still molten Earth was struck a glancing blow by a Mars-sized protoplanet, which scientists have named Theia. This was not a simple collision. It was an apocalyptic event that would have vaporized rock and melted the entire surface of our planet. Theia itself was utterly obliterated upon impact. Its dense iron core would have sunk and merged with Earth's own core, while a colossal plume of vaporized rock, a mixture of material from Theia's mantle and Earth's own mantle, was flung into orbit around our devastated planet. This seething, donut-shaped cloud of superheated material, known as a cynosure, is where the magic happened. Within this cloud, the vaporized rock began to cool and clump together, accreting through countless smaller collisions. Within, astonishingly, just a few hundred years, a blink of an eye in geological time, this debris coalesced to form our Moon. This process perfectly explains the isotopic similarities. The material came primarily from the mantles of both worlds. It also explains the lack of a large iron core. Theia's core was absorbed into Earth, leaving the Moon to form from the surrounding mantle debris. The energy of the impact also explains why volatile elements like water and zinc are so depleted on the Moon compared to Earth. The incredible heat would have boiled them away into space. But even this beautifully violent story is not without its own modern tensions. Advanced computer simulations have shown that for the impact to create a Moon with the exact chemistry we see, Theia would have needed an isotopic composition nearly identical to early Earth. This is statistically very unlikely, as most objects in the early solar system had distinct signatures. Was Theia an isotopic twin of Earth, formed at a similar orbital distance, or is our understanding of the physics of the impact still incomplete? Some newer models suggest a far more violent, high-energy impact that led to a more thorough mixing of materials, potentially allowing for a Theia with a different composition to still yield an Earth-like Moon. The debate continues to rage, fueled by ever more detailed computer models and new analyses of the Apollo samples. Each mission proposal to send new rovers to the lunar far side, or to drill deeper into its crust, carries the hope of finding a rock that might still hold a chemical memory of Theia, a final clue to the most important day in Earth's history. The Moon is more than our companion in the sky. It is the scar of our violent birth, a constant reminder that our peaceful world was forged in a cosmic collision of unimaginable ferocity. While the violent birth of our moon speaks to the dynamic chaos of the early solar system, a more modern mystery lurks in the frigid, silent darkness far beyond the orbit of Neptune. This is the realm of the Kuiper Belt, a vast donut-shaped disk of icy worlds and debris that is the source of many short-period comets. For decades, our models of solar system formation have painted a picture of this region. As you move outward from the Sun, the number of these icy bodies should gradually decrease in a smooth and predictable way. But the reality, as we've begun to map this distant frontier, is utterly different. Astronomers have found a sudden, precipice-like drop-off in objects at a distance of about 50 astronomical units from the Sun. One moment you're detecting a healthy population of frozen worlds, and the next you find almost nothing. This boundary has been dubbed the Kuiper Cliff, and its existence challenges our most fundamental ideas about how our cosmic neighborhood came to be. The most straightforward explanation is that our observations are simply incomplete. This is the observational bias argument. The Kuiper Belt is an incredibly difficult place to survey. Objects that are faint move slowly against the background stars and require immense light-gathering power and patience to detect. Perhaps the cliff is just an illusion, a zone where our current telescopes can no longer spot the smaller, darker objects that surely exist. However, as our technology has improved with telescopes like Subaru and Pan-STARRS, this argument has become harder to sustain. We are now finding objects well beyond the 50 mark, like the distant dwarf planet Sedna, which has a highly elongated orbit taking it out to over 900 astronomical units. The problem isn't that we can't find things past 50, it's that we find a startlingly low number of them compared to what our models insist should be there. The cliff appears to be a real feature, not a trick of the light. This forces astronomers to consider more dramatic physical explanations. The most tantalizing possibility is that the Kuiper Cliff is the gravitational signature of an unseen massive planet. This is the same line of reasoning that has led to the search for the hypothesized Planet 9. The idea is that a planet several times the mass of Earth, orbiting hundreds of astronomical units from the Sun, could have a profound influence on the distant Kuiper Belt. As it travels along its elongated path, its immense gravity would act like a shepherd, clearing out a vast swath of space. It could scatter smaller objects, ejecting them from the solar system entirely or shepherding them into orbits that avoid its path, thereby creating a sharp boundary in the population of objects we can observe. The Kuiper Cliff could be the empty pasture, and the unseen planet is the rancher that cleared it. Yet another fascinating theory looks not outward for an answer, but backward in time. Perhaps the Kuiper Belt was once much more populated in its outer regions, but something happened in the solar system's youth to strip it bare. Our Sun did not form in isolation. It was born in a stellar nursery amidst thousands of other sibling stars. It's possible that a rogue star passed uncomfortably close to our infant solar system billions of years ago. The gravitational tug from this stellar intruder could have plucked a vast number of icy bodies from the outer Kuiper Belt, flinging them into interstellar space and leaving behind the depleted region we see today. In this scenario, the Kuiper Cliff is a fossilized record of a traumatic close encounter, a ghostly imprint of a long-lost stellar cousin. Alternatively, the culprit might not have been a single dramatic event, but a more subtle process. Some models suggest that the protoplanetary disk of dust and gas from which our solar system formed simply had a built-in edge, perhaps due to the specific conditions in that part of the nebula. It's also possible that the gravitational influences of the giant planets, particularly Jupiter and Neptune, during an early period of planetary migration, resonantly swept the outer disk clean, effectively creating a hard boundary to planet formation. The Kuiper Cliff, therefore, wouldn't be a mystery to be solved, but a direct and expected consequence of how our planetary system was assembled. Resolving this mystery is more than just an exercise in cosmic cartography. Understanding the true nature and population of the Kuiper belt is crucial for validating our models of planetary system formation. If our own solar system doesn't follow the rules we've written, how can we accurately interpret the disks of dust and debris we see around other stars? The Kuiper cliff stands as a stark reminder that even in our own celestial backyard, there are profound secrets waiting to be uncovered, and the most powerful explanations might still be hiding in the perpetual twilight at the edge of our sun's influence. This absence isn't just a minor accounting error, it's a fundamental problem. We have a detailed inventory of all the ordinary matter we can directly see: stars, galaxies, the hot gas in galaxy clusters, and the cold hydrogen gas drifting in space. When we add it all up, it accounts for only about 60 to 70% of the baryonic matter that our most trusted models insist must exist. For decades, this meant that roughly 1/3 of the normal stuff in the universe was simply unaccounted for, hiding somewhere in the vast cosmic voids between the glittering islands of galaxies. This missing matter became one of cosmology's most stubborn cold cases. The prime suspect in this mystery is a form of matter so elusive it has evaded detection until very recently: the warm-hot intergalactic medium, or WIM. Imagine the universe isn't mostly empty space, but is instead structured like a colossal sponge. The bright galaxies and galaxy clusters are the dense, solid parts of the sponge, while the vast, seemingly empty spaces are actually filled with a tenuous web of incredibly hot, ionized gas. This is the WIM. It's not a cold, dark void. It's a superheated highway of plasma, with temperatures ranging from hundreds of thousands to millions of degrees Celsius. This immense heat prevents the gas from collapsing under its own gravity to form stars and galaxies, and it also makes it nearly invisible to traditional telescopes. It's too hot to emit visible light and too diffuse to block the light from objects behind it significantly. It's the ultimate cosmic ghost, a pervasive presence that has stubbornly refused to reveal itself. So how do you find something that is practically invisible? Astronomers have had to become detectives, developing ingenious and indirect methods to trace the WIM faint signature. The most successful technique involves using the brightest beacons in the universe, quasars. These are the intensely luminous cores of distant galaxies, powered by supermassive black holes greedily consuming matter. By pointing powerful X-ray and ultraviolet telescopes at these distant quasars, scientists can analyze their light after it has journeyed for billions of years through the cosmic web. As this light passes through filaments of the WIM, the superheated gas acts like a filter. Atoms within the WIM, particularly highly ionized oxygen, nitrogen, and neon, will absorb very specific wavelengths of this light. Each absorption line is like a fingerprint, a tiny dip in the quasar's spectrum that betrays the presence, temperature, density, and even the velocity of the invisible gas that caused it. It's a painstaking process akin to identifying the composition of a distant fog by analyzing the precise pattern of colors missing from a searchlight beam after it passes through. This meticulous detective work is finally paying off. In recent years, observations from telescopes like the European Space Agency's XMM Newton and NASA's Hubble Space Telescope have begun to find these telltale absorption lines. In 2019, a team of astronomers made a landmark announcement. They had used the light from a distant quasar to map a missing baryon filament, finding the long-sought signature of oxygen atoms heated to approximately 1 million degrees Celsius. This was a monumental step, providing some of the most direct evidence yet that the WIM is indeed the hiding place for a significant portion of the universe's missing ordinary matter. These observations suggest the WIM is not a uniform haze but a structured network of filaments, exactly as predicted by simulations of the cosmic web. However, confirming the existence of a few filaments is a far cry from closing the case entirely. The challenge now is to move from these few precious detections to a full census. We need to know how this material is distributed throughout the entire universe and confirm that there is indeed enough of it to solve the missing baryon problem completely. This requires a new generation of instruments with even greater sensitivity. Upcoming X-ray observatories like ESA's Athena and NASA proposed Lynx mission are being designed with this specific goal in mind. Their unprecedented resolution and collecting power will allow them to study the absorption lines from numerous quasars simultaneously, effectively allowing us to create a three-dimensional map of this hidden cosmic infrastructure for the very first time. Solving the mystery of the missing baryons is about more than just balancing a cosmic ledger. It's a critical test of our entire model of the universe's evolution and structure. The fact that our predictions from the Big Bang were so precise and that we are now finally finding the matter exactly where our model said it should be is a powerful validation of our understanding of cosmic history. It confirms that we are on the right track, piecing together the story of how the primordial soup of particles evolved into the magnificent web of galaxies we see today. The WIM represents the final chapter in the story of ordinary matter, the last strands of the cosmic skeleton that holds the universe together, and we are only just beginning to bring it into focus. But all of these grand structures, from the cosmic web to the missing matter within it, are built from the most fundamental building blocks, the atoms forged in the universe's first fiery moments. And here, in the creation story of the lightest elements, we find a small but glaring error in our cosmic accounting. We call it the lithium problem. Our most successful and precise story of the universe's origin is the Big Bang model. A critical part of this model is Big Bang nucleosynthesis, which describes how the first atomic nuclei were assembled in the first 20 minutes of existence. In the unimaginably hot and dense conditions of that infant cosmos, protons and neutrons fused together, primarily forming hydrogen, helium, and trace amounts of lithium. We can run the physics of these nuclear reactions backwards with incredible accuracy. The predicted abundance of helium-4 matches what we observe in the oldest regions of the universe almost perfectly. The amount of deuterium, a heavy form of hydrogen, also aligns beautifully with the models, serving as a powerful confirmation that we understand the basic conditions of that first nuclear forge. But then there's lithium-7. According to the meticulous calculations of Big Bang nucleosynthesis, the primordial universe should have produced about 3 times more lithium-7 than what we actually find when we look at the oldest stars in our galaxy. These ancient stellar relics, known as population 2 stars, are like cosmic time capsules. They formed from nearly pristine gas that hadn't been contaminated by later generations of element-forging stars, so their atmospheres should preserve the chemical signature of the Big Bang itself. Yet when astronomers point their spectrographs at these stars, they consistently measure a lithium abundance that is only 1/3 of what our theories insist should be there. It's as if the universe's recipe book has a misprint for one crucial ingredient. So where did all the lithium go, or was it never made in the amounts we think? Scientists have been chasing down solutions to this puzzle for decades, and the suspects generally fall into 2 camps. The first possibility is that our understanding of the nuclear physics itself is incomplete. Perhaps there were unknown or poorly measured nuclear reaction rates at play in the early universe that consumed lithium-7 faster than it could be produced. Some theorists have proposed the existence of a hypothetical new particle, like a certain type of supersymmetric particle, that could have interacted with the primordial soup and altered the reaction pathways, effectively erasing the expected lithium. This would be a thrilling hint of physics beyond the standard model, a ghost from the first moments of time influencing the chemistry of the cosmos. The other major line of investigation looks not at the creation of lithium, but at its potential destruction. Maybe the Big Bang did produce the correct amount of lithium-7, but something has been systematically destroying it inside these ancient stars over the past 13 billion years. Stars are not static containers, they are dynamic furnaces. Could some unknown mixing process in the stellar interiors have dragged the surface lithium down into hotter layers where it was easily fused into heavier elements? Some models suggest that gravitational settling or waves generated deep within the star could have slowly depleted the lithium abundance we measure today. If this is the case, then the problem isn't with the Big Bang, but with our interpretation of the stellar forensic evidence. The challenge in solving this is the immense difficulty of peering into the hearts of these ancient stars. We can't directly observe their internal processes. We can only infer them from complex computer models and the delicate fingerprints they leave in the starlight. New observational techniques are constantly refining our measurements, and the hunt continues for even older, more pristine stars that might hold a clearer record. The lithium problem is a classic scientific conundrum. It's a tiny discrepancy, a single data point that refuses to fit, and yet its resolution could either reinforce our confidence in the Big Bang or force us to rewrite the physics of the universe's very first minutes. It stands as a powerful reminder that sometimes the smallest mysteries can point toward the biggest truths. But this profound revelation leads us to an even deeper question. What is the nature of this mysterious force pushing the cosmos apart? The leading candidate is a concept that Albert Einstein himself once toyed with and then famously discarded, calling it his greatest blunder. He called it the cosmological constant, a property inherent to the vacuum of space itself. The idea is that empty space is not truly empty. It is a seething, bubbling foam of quantum activity where virtual particles constantly flicker in and out of existence. This quantum fizz is thought to possess a kind of energy, and this energy of nothingness exerts a negative pressure, causing the very fabric of space-time to stretch. In this view, dark energy is a constant, unchanging force woven into the universe's foundation, with a strength determined by a single number. However, this elegant idea faces a monstrous problem. When physicists attempt to calculate the predicted energy density of this quantum vacuum using our current theories, the value they get is wrong. Not just a little off, but wrong by a factor of 10 to the power of 120. This is not just the worst prediction in the history of science. It is a number so colossally incorrect that it points to a fundamental gap in our understanding of physics. This staggering discrepancy has led scientists to explore other, even more exotic possibilities. Perhaps dark energy is not a constant after all, but a dynamic field that changes over time. This concept, dubbed quintessence after the classical fifth element, suggests that this repulsive force could be weakening or strengthening, which would dramatically alter the universe's ultimate fate. The implications of an accelerating universe are as profound as they are sobering. If dark energy continues to dominate, it paints a picture of a future known as the Big Freeze or heat death. In this scenario, the acceleration will continue unchecked. Distant galaxies will be pushed away from us so quickly that their light will never be able to reach us. Over trillions of years, the observable universe will effectively shrink to include only our own local group of gravitationally bound galaxies. Beyond that, there will be only an ever-expanding, impenetrable darkness. Within those isolated islands, star formation will eventually consume all the available gas, and one by one, the stars will burn out. The universe will become a cold, dark, and increasingly empty place, a vast cosmic graveyard where the only remaining activity is the slow decay of particles and the occasional flash of a dying black hole. This is not a violent end, but a quiet, lonely fading away, a testament to the power of a mysterious force we are only just beginning to comprehend. And yet, for all the potential and promise held within these billions of worlds, the cosmos remains profoundly and perplexingly silent. We have never received a confirmed message, never found an artifact, never seen an unmistakable sign of another technological civilization. This contradiction between the high probability of alien life and the utter lack of evidence for it is one of the most enduring puzzles in science, a riddle so significant it has its own name, the Fermi Paradox, often referred to as the Great Silence. The paradox gets its power from a simple question of scale. The Milky Way galaxy is roughly 13 billion years old. Our solar system is a relative newcomer at about 4.5 billion years old. This means there was a multi-billion-year head start for other civilizations to arise, develop technology far beyond our own, and eventually expand across the galaxy. Even traveling at a modest fraction of the speed of light, a single motivated civilization could colonize the entire Milky Way within a few tens of millions of years, a mere blink of an eye on the cosmic calendar. The mathematics suggests the galaxy should be teeming with life, buzzing with activity. The observational evidence, however, suggests a quiet, empty void. So, where is everybody? Scientists and philosophers have proposed a vast spectrum of solutions to this haunting silence, and they range from the comforting to the utterly terrifying. One of the most prominent ideas is the rare Earth hypothesis. This argument suggests that while simple microbial life might be common, the emergence of complex, intelligent, technological life requires an incredibly precise and unlikely chain of events. It's not just about being in the habitable zone. It might require a large moon to stabilize the planet's axial tilt and prevent chaotic climate shifts, a Jupiter-like outer planet to act as a gravitational shield deflecting comets and asteroids, the right kind of galactic orbit that avoids sterilizing supernova, and the correct plate tectonics to regulate carbon cycles. In this view, Earth isn't a typical rocky world. It might be a cosmic lottery winner, a one-in-a-billion fluke, and we are simply alone in our galactic neighborhood. On the opposite end of the spectrum lies a more unsettling set of possibilities, often grouped under the grim banner of the Great Filter. This theory proposes that there is some kind of barrier, a nearly insurmountable challenge that prevents life from progressing to the stage of interstellar communication or colonization. The crucial and frightening question is where this filter lies. Is it behind us? Perhaps the leap from simple prokaryotic cells to complex eukaryotic life was a one-in-a-billion event that took billions of years to occur on Earth by sheer chance. If the Great Filter is in our past, it means we are impossibly lucky to have made it this far, but we are also likely alone. The more chilling possibility is that the Great Filter is ahead of us. It could be that almost all advanced civilizations inevitably destroy themselves upon discovering certain technologies, whether through nuclear war, climate catastrophe, engineered pandemics, or a future technology like misaligned artificial intelligence that we haven't even conceived of yet. In this scenario, the cosmic silence is a grave warning, a galaxy full of tombstones of species who failed to overcome their own self-destructive tendencies. Other solutions are less apocalyptic but equally mind-bending. Perhaps intelligent civilizations don't vanish, they simply transcend. They may develop technology that moves beyond our crude methods of radio transmission and physical spacecraft, uploading their consciousness into virtual realities or evolving into forms of pure energy that are completely undetectable to our primitive instruments. We might be like ants at a picnic, unaware of the vast, complex civilization buzzing around us because we lack the senses to perceive it. Then there's the zoo hypothesis, which suggests that advanced civilizations are out there and aware of us, but they are deliberately avoiding contact, perhaps to allow us to develop naturally without interference, like observers in a cosmic wildlife preserve. There are also more practical, physical explanations. Maybe interstellar travel is simply too difficult, too expensive, or too slow to be practical for anyone. The vast distances and incredible energies involved could represent a hard physical limit that not even the most advanced species can overcome. Or perhaps the timescales are the real issue. Civilizations might bloom and fade so quickly that the probability of two of them existing and being technologically advanced at the same exact cosmic moment is vanishingly small. We could be listening for signals, but the broadcasts of a civilization 100 light years away might have ended 1,000 years before we ever started listening. Ultimately, the Great Silence holds up a mirror to humanity. In searching for others, we are forced to confront our own future and our own nature. The void speaks volumes not by what it says, but by what it doesn't. Every possible solution to the Fermi Paradox tells a different story about life, intelligence, and the universe itself. Are we a miracle, a warning, or simply early to the party? The search continues, and with every silent, star-filled night, we are reminded that the greatest answer we could ever receive is not a message, but the profound weight of the question itself. While we scan the cosmos for whispers of distant intelligence, some believe the proof has been silently circling above our heads for millennia. This brings us to one of space's most enduring and tantalizing modern legends, the tale of the Black Knight satellite. The story goes that there is an ancient, alien object of unknown origin in near-polar orbit around Earth, a silent sentinel that has been watching our world for 13,000 years. It's been linked to mysterious radio signals, hailed as evidence of prehistoric alien contact, and cited as the ultimate government cover-up. The reality, however, is a fascinating case study in how myths are born from a collage of misunderstood events, genuine space history, and our powerful desire to find patterns in the unknown. The legend truly took hold in the 1950s when various newspapers reported that the U.S. Air Force had detected a mysterious, dark object in orbit. These stories were likely sparked by the fear and excitement of the early space race, but the myth retroactively gained immense weight a few years later when it was connected to a much older event. In 1899, the brilliant inventor Nikola Tesla was conducting experiments with his high-voltage radio transmitter in Colorado Springs. He reported receiving a peculiar, repeating signal that he couldn't explain, and he even mused that it might be an attempt at communication from another world. Decades later, amateur radio operators listening on similar frequencies also reported strange, coded signals. Proponents of the Black Knight theory later wove these disparate events into a single narrative, claiming Tesla was the first to hear the satellite's transmission, a story that sounds compelling until you examine the actual objects mistaken for this phantom. So what were people actually seeing? The single most famous piece of evidence is a photograph taken during the 1998 STS-88 mission, the first space shuttle flight to dock with the new International Space Station. The image shows a bizarre, angular black object against the curvature of the Earth, looking utterly alien and out of place. This wasn't an alien probe, it was a thermal blanket. The crew had lost the protective cover for an equipment module during a spacewalk, and it slowly tumbled away, creating a perfect, though entirely mundane, photographic mystery. The human mind is exceptionally good at finding familiar shapes in random patterns, a phenomenon called pareidolia, which is why we see faces in clouds or figures in shadows. This lost blanket became the face of the Black Knight. The myth also draws its power from a very real and very crowded celestial environment. Earth is enveloped in a cloud of space debris, ranging from flecks of paint to spent rocket boosters and defunct satellites. Many of these objects have unusual orbits and tumble erratically, reflecting sunlight in strange ways that can look utterly perplexing to a ground-based observer. In the early days of spaceflight, tracking was far less precise, and objects would often appear on radar that couldn't be immediately identified, fueling speculation about secret military projects or, more excitingly, extraterrestrial visitors. The name Black Knight itself wasn't plucked from thin air. It was the title of a real British launch program in the late 1950s, a series of experimental rockets that had nothing to do with alien technology but provided a perfect, ominous name for the legend to adopt. Why does this story persist so stubbornly in the face of such clear debunking? It taps into a deep and powerful human archetype, the idea of a hidden truth, a secret history that the authorities are keeping from the public. The notion that an ancient artifact is orbiting our planet just out of reach is a profoundly romantic and thrilling concept. It transforms the cold, impersonal void of space into a place of mystery and potential discovery, a canvas onto which we can project our hopes and fears about our place in the universe. The Black Knight is more than just a story about space junk. It's a modern myth, a testament to our endless fascination with the sky and our unwavering desire to believe that we are not alone, and that evidence of others is quite literally hanging right over our heads. Just when we thought we had our own solar system figured out, the universe sent a visitor that challenged everything. In October 2017, astronomers at the University of Hawaii made an extraordinary discovery using the Pan-STARRS 1 telescope. They spotted an object moving so fast that its trajectory could only mean one thing: it was not from here. It was the first confirmed interstellar object ever detected passing through our solar system. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And this messenger was profoundly strange. The anomalies began with its shape. Based on the way its brightness changed dramatically as it tumbled through space, astronomers deduced that Oumuamua was highly elongated, shaped like a pancake or a cigar, with an estimated length perhaps 10 times its width. This was unlike any known asteroid or comet from our own system, which tend to be more lumpy and rounded. But the real shock came months after it had already passed its closest approach to the Sun and was speeding away. As astronomers tracked its path, they noticed something impossible to ignore. It was accelerating, not just from the Sun's gravity, but as if an extra, unseen force was giving it a gentle push. This is standard behavior for comets. As they approach the Sun and heat up, ices on their surface turn to gas, creating jets that act like natural rocket engines. This process is called outgassing. The problem was, Oumuamua showed absolutely no visible signs of this activity. No dusty coma surrounded it, no tail of gas streamed behind it. It was as dark and spectrally featureless as a cosmic rock could be, offering no hint of the volatile materials that should have been fueling its unexpected acceleration. This combination of bizarre traits, its interstellar origin, its extreme shape, and its non-gravitational acceleration without any visible outgassing, triggered a firestorm of scientific debate and public fascination. How could something accelerate without the telltale signs of a comet? The scientific community scrambled for natural explanations. One leading idea proposed that perhaps Oumuamua was a fractal-like aggregate of dust, a so-called dust bunny from another star system, so porous and lightweight that radiation pressure from the Sun itself could have provided the push. Others suggested it could be a shard of a Pluto-like planet that was torn apart by its home star's gravity, a chunk of solid nitrogen ice that would sublimate without leaving much of a visible trace. The most developed natural theory, published in 2023, suggests Oumuamua could have been a hydrogen iceberg. The idea is that in the cold, dense cores of giant molecular clouds, molecular hydrogen can freeze solid. A chunk of this solid hydrogen, when ejected into interstellar space and later warmed by the Sun, would sublimate. Because hydrogen gas is invisible to our telescopes, this outgassing would provide the necessary thrust while leaving no observable coma or tail, neatly explaining the acceleration. However, critics point out the immense challenge of such an object surviving a journey that could last millions of years bathed in cosmic radiation without simply evaporating away into nothingness long before it reached us. The failure of any single natural explanation to provide a universally accepted answer opened the door to more speculative possibilities. Most famously, Harvard astronomer Avi Loeb proposed that Oumuamua's behavior could be explained if it were not a natural object, but a piece of advanced alien technology. perhaps a light sail, a form of propulsion that uses the radiation pressure from starlight to navigate the galaxy. In this scenario, its unusual acceleration and strange, flat shape would be consistent with a designed object, a discarded artifact or a derelict probe from a distant civilization. While Loeb himself has consistently stated this is a possibility that should be discussed rather than a definitive conclusion, the idea captured the global imagination and ignited a fierce debate about how scientists should approach such extraordinary claims. The core of the scientific resistance to the light sail hypothesis is not a closed-minded dismissal but a strict application of Occam's razor, the principle that the simplest solution is usually the correct one. Invoking an extraterrestrial civilization is the most complex explanation possible. It should only be considered after all natural avenues have been thoroughly exhausted. For most astronomers, we are not yet at that point. The fact that we lack a perfect natural model for Oumuamua says more about the infancy of interstellar object science than it does about the existence of aliens. Before 2017, we had exactly 0 data points on what material from other star systems might look like. Oumuamua was our first, and its strangeness may simply reflect our own ignorance of the true diversity of objects that drift between the stars. This is why the legacy of Oumuamua is not a definitive answer but a profound shift in perspective. It was a wake-up call that our solar system is not an isolated island. The galaxy is likely filled with such interstellar nomads constantly passing through our neighborhood. Its fleeting visit taught astronomers that they need to be ready for the next one. New projects like the Vera C. Rubin Observatory's legacy survey of space and time are designed to systematically scan the skies, promising to find many more of these visitors in the coming years. Perhaps then, with a larger sample of interstellar objects to study, the mystery of Oumuamua will finally be solved. It will be remembered not for what it proved, but for the questions it forced us to ask, proving that sometimes the most significant discoveries are the ones that leave us the most perplexed. While our gaze has been drawn to enigmatic visitors and the silent voids between stars, some of the universe's most compelling mysteries are broadcast from our own galactic backyard. At the very heart of the Milky Way, a region of immense density and ferocious energy, astronomers have detected a signal that defies easy explanation. This mystery is known as the galactic center excess, and it begins with a persistent, faint glow of high-energy gamma-ray light that shouldn't be there. This story starts with a telescope designed to see the universe in a whole new light. NASA's Fermi Gamma-Ray Space Telescope, launched in 2008, has been mapping the sky in gamma rays, the most energetic form of light in the cosmos. Gamma rays are produced by the universe's most extreme phenomena, the violent deaths of massive stars, the powerful jets of supermassive black holes, and the collisions of subatomic particles moving at nearly the speed of light. As Fermi meticulously scanned the heavens, it built up a detailed picture of the gamma-ray sky. But when scientists looked toward the crowded core of our galaxy, they found something unexpected. There was a diffuse, roughly spherical glow of gamma-ray emission surrounding the galactic center, extending thousands of light-years above and below the galactic plane. This glow was in addition to the expected gamma rays from known sources like pulsars and the interactions of cosmic rays with interstellar gas. It was an excess, a surplus of radiation with no immediately obvious cause. The hunt was on to identify the source of this mysterious energy. The two most compelling hypotheses that emerged pitted established astrophysics against the frontier of particle physics, offering two very different visions of our galaxy's core. The first and more conventional explanation points to a vast, unseen population of incredibly ancient stars. These would be millisecond pulsars, the rapidly spinning, ultra-dense corpses of suns that have been reanimated by siphoning material from a companion star. A single millisecond pulsar is a weak gamma-ray source, but the theory suggests that thousands of them, too faint and too close together for Fermi to resolve individually, could collectively produce the observed haze of excess radiation. The galactic center is the oldest part of the Milky Way, a natural place for a dense swarm of such ancient stellar remnants to have accumulated over billions of years. If this is the answer, it would be a fascinating discovery in its own right, revealing a previously invisible structure at the heart of our galaxy. The second, and far more thrilling, possibility is that the galactic center excess is nothing less than the first indirect detection of dark matter. This idea hinges on the nature of what dark matter might be. The leading theoretical candidate is a type of weakly interacting massive particle, or WIMP. According to some models, when two WIMP collide, they could annihilate each other, transforming their mass directly into energy and producing a shower of standard model particles, including gamma rays. The density of dark matter is thought to be highest in the gravitational well at the center of the galaxy. If WIMP are real, this is exactly where they should be colliding most frequently, creating a spherical halo of gamma-ray light that would match the excess observed by Fermi almost perfectly. The energy spectrum of the observed gamma rays, their specific distribution across different energy levels, bears a striking resemblance to the signature predicted for WIMP annihilations. For particle physicists and cosmologists, this is a tantalizing clue that we might be seeing the ghostly fingerprint of the universe's most elusive substance. The debate between these two explanations is fierce and remains unresolved. Proponents of the pulsar argument have scoured the data for proof. They point to statistical analyses suggesting the excess is not perfectly smooth, but might be lumpy, which would be consistent with it being composed of many point sources too faint to see individually. However, follow-up observations with radio telescopes, which should be able to detect the radio waves from such a dense population of pulsars, have so far come up empty, failing to find the number of pulsars needed to explain the signal. This absence of corroborating evidence keeps the dark matter hypothesis very much alive. The truth may ultimately lie in improved technology and more sophisticated analysis. The next generation of gamma-ray telescopes with higher resolution and sensitivity might finally be able to resolve individual point sources within the glow, definitively confirming the pulsar theory. Conversely, if the excess remains stubbornly smooth and diffuse, the case for dark matter annihilation will grow significantly stronger. The galactic center excess is a perfect example of a modern astronomical mystery, where the signal is clear but its interpretation requires us to choose between the known unknowns of astrophysics and the unknown unknowns of fundamental physics. It reminds us that sometimes the answers to the universe's biggest questions are hiding in plain sight, radiating from the dark heart of our own galactic home. Yet if the mysteries of interstellar visitors and galactic center radiation feel distant, consider one that unfolded a mere 38 million miles away on our closest planetary neighbor. In the sweltering, acid-drenched skies of Venus, a gas was detected that had no business being there, a discovery that for a brief, electrifying moment seemed to point to the possibility of life next door. This is the story of the Venus phosphine mystery, a saga that perfectly captures the thrilling and often tumultuous process of scientific discovery. It all began in September 2020, when a team of astronomers led by Jane Greaves from Cardiff University made a stunning announcement in the journal Nature Astronomy. Using two of the world's most powerful radio telescopes, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile, they had detected the spectral signature of phosphine gas in the temperate cloud decks of Venus. Now, phosphine itself is a simple molecule, one phosphorus atom bonded to 3 hydrogen atoms, but its presence on a rocky world is anything but simple. Here on Earth, phosphine is exclusively associated with life. Anaerobic microbes deep in swamps and animal guts produce it, and it's notoriously difficult to create through any known non-biological process that doesn't involve immense heat and pressure, like those found deep within the mantle of a planet or in the atmosphere of a gas giant. On Venus, it was found floating about 30 miles above the surface, in a layer of the atmosphere where the temperature and pressure are surprisingly Earth-like. The implication was as shocking as it was irresistible. Could this be a biosignature? Could there be microbial life floating in the Venusian clouds? The scientific community and the public erupted with a mixture of exhilaration and intense skepticism. The idea of life on Venus is not new. Astronomers like Carl Sagan had speculated about it decades ago. The planet's surface is a hellscape with temperatures hot enough to melt lead and a crushing atmospheric pressure 92 times that of Earth. But up in the clouds, conditions are far more hospitable. The discovery seemed to fit a tantalizing narrative. Extremophile microbes, eking out an existence in aerial droplets, could be producing this gas as a byproduct of their metabolism. It was a story almost too incredible to believe, and believe it, many scientists did not. The controversy ignited immediately, focusing on two critical points: the data itself and the alternatives to biology. Other research teams attempted to reanalyze the same data sets. Some failed to find the phosphine signal at all, suggesting it might have been a statistical fluke or an artifact of how the complex data was processed. The original team held firm, refining their analysis and continuing to assert their detection, but the shadow of doubt had been cast. The second, and perhaps more powerful, line of attack came from researchers hunting for abiotic explanations. If it wasn't life, what could it be? The challenge was to find a way to make phosphine on Venus that didn't require biology. Could unknown Venusian geology or atmospheric chemistry be responsible? Perhaps volcanic eruptions were belching phosphorus containing compounds into the atmosphere, where subsequent chemical reactions could somehow form phosphine. Maybe sunlight interacting with Venusian dust particles or sulfuric acid droplets could trigger a previously unknown photochemical process. The problem was that every abiotic model proposed fell short. None could produce phosphine in the quantities reportedly observed without invoking a series of unlikely and unproven chemical reactions. The quest for answers demanded a closer look, and so the world's space agencies turned their eyes back to a planet that had been somewhat neglected since the era of Soviet Venera landers. New missions were proposed and accelerated. NASA greenlit its Da Vinci and Veritas missions, while the European Space Agency planned its Envision orbiter, all designed in part to study the planet's atmosphere and geology with unprecedented precision. In the meantime, follow-up observations from Earth continued. A team using the Stratospheric Observatory for Infrared Astronomy, or SOFIA, a telescope mounted on a specially modified aircraft, went looking for the phosphine signature. After several meticulous flights, they found nothing. Their non-detection added significant weight to the argument that the original signal might have been an error. Yet the story refuses to die. The original researchers and other teams have published additional papers, sometimes claiming new detections and standing by their methods. The scientific process is now fully engaged in what it does best, a slow, meticulous, and often contentious back and forth of claim and counterclaim, analysis and reanalysis. The phosphine mystery may not end with a definitive discovery of alien life, but its true value may be even greater. It has forced us to look at Venus with new eyes, to question our assumptions about where life could exist, and to remember that our nearest planetary neighbor still holds profound secrets. It is a powerful lesson in humility, showing that even in our own celestial backyard, the universe is still capable of delivering the most wonderful and confounding surprises. Now let's journey into the heart of the atom itself, to a mystery that challenges the very rules governing how matter holds itself together. For decades, nuclear physics has been guided by a seemingly unbreakable law. You cannot have a particle made solely of neutrons. The atomic nucleus is a delicate balance held intact by the strong nuclear force, the mightiest force in nature, which acts like a powerful glue binding protons and neutrons together. But protons, with their positive charge, naturally repel each other. It's the neutral neutrons that often play the crucial role of mediators, easing the tension between protons to help keep the nucleus stable. Because of this, the idea of a nucleus with only neutrons, with no protons at all to hold onto, has been considered impossible. The nuclear forces simply shouldn't be able to bind them. A lone neutron itself decays into a proton in about 15 minutes, so a group of them should fly apart instantly. This is why the hypothetical tetraneutron, a stable particle consisting of 4 bound neutrons, has been the stuff of physics legend. A ghost that, if real, would force us to tear up the textbook and start a new chapter. The first tantalizing whisper of this phantom particle emerged in 2002 from a particle accelerator experiment in France. Researchers at the Ganel facility were not looking for it. They were studying the properties of unstable, neutron-rich nuclei. Their method involved firing a beam of lithium isotopes at a carbon target and analyzing the debris from the high-energy collisions. In the aftermath of these miniature cosmic crashes, they observed signals that were incredibly difficult to explain. The data suggested that for a fleeting moment, 4 neutrons had briefly come together and behaved as a single, unified particle before disintegrating. The statistical significance was low, and many in the community were deeply skeptical, attributing the signal to a chance alignment of 4 separate, non-bound neutrons. It was an intriguing anomaly, but not yet a discovery. The plot thickened dramatically over a decade later. In 2016, a Japanese team at the Riken Research Institute conducted a more precise follow-up experiment. They used a different approach, colliding a beam of helium-8, an extremely unstable, neutron-heavy isotope, into a target of regular helium-4. The reaction they were looking for was designed to be cleaner. The collision would, in theory, knock out the 2 protons and 2 neutrons from the stable helium-4 core, leaving behind just the 4 neutrons from the helium-8. Once again, the detectors registered a clear, sharp resonance, a telltale energy signature that indicated the 4 neutrons were interacting strongly with each other, hinting at a bound state that lasted for a breathtakingly short time, just 10 to the power of -22 seconds. This was not a long-lived object, but a resonance, a fleeting whisper of a particle that momentarily existed against all odds. Why is the mere suggestion of a tetraneutron so revolutionary? It strikes at the very heart of our understanding of the strong force. Our current models, incredibly successful at explaining everything from the stability of gold to the power of the sun, simply do not allow for a bound state of pure neutrons. The forces involved are not attractive enough to overcome the inherent instability. If the tetraneutron is confirmed to be a genuine resonance, or even more astonishingly, a stable particle, it means there is a facet of the strong nuclear force we have completely missed. It could imply that under certain, very specific conditions, neutrons can form a new kind of correlation or exhibit a property we haven't yet dreamed of, effectively creating a new state of nuclear matter. This wouldn't just be a new particle, it would be a new principle. The scientific pursuit of the tetraneutron is a masterclass in experimental rigor. The challenge is immense because you cannot simply put neutrons in a bottle and watch them. They are elusive and decay rapidly. Researchers must infer their existence from the intricate fingerprints they leave in sophisticated detectors, painstakingly ruling out every other possible explanation for the signals they see. Each new experiment is a refinement, a more precise attempt to corner this phantom. The quest continues at laboratories around the world, with teams developing ever more sensitive techniques to either finally capture definitive proof or firmly relegate the tetraneutron to the realm of fascinating statistical flukes. Its existence hangs in a delicate balance, much like the particle itself, representing one of the most fundamental and exciting challenges in modern physics. A tiny, subatomic key that could unlock a door to a completely new understanding of the forces that build our reality. But if the axis of evil shows us that the universe might have a preferred direction on its largest scales, our next discovery suggests it might also have a scar, a vast, cold bruise on the sky that defies any simple explanation. This is the mystery of the CMB cold spot, a perplexing anomaly in the afterglow of the Big Bang that has sparked theories ranging from the incredible to the truly otherworldly. Located in the constellation Eridanus, the cold spot isn't just a slightly cooler patch. It was first identified with high confidence by NASA's Wilkinson microwave anisotropy probe and later confirmed by the Planck satellite. It's a circular region of the cosmos about 70 degrees across, an enormous expanse on the sky where the temperature of the cosmic microwave background is roughly 70 microkelvins colder than the average surrounding area. Now the CMB is already filled with tiny temperature fluctuations, hot and cold spots that represent the seeds of future galaxies, but the cold spot is different. It's a colossal outlier, a statistical anomaly so significant that the odds of it appearing randomly in an otherwise isotropic universe are estimated to be as low as 1 in 200. It's a feature that demands a physical explanation, a cause for this giant cosmic chill. The most straightforward and conservative explanation is that it's not a feature of the primordial CMB at all, but something in the foreground. Imagine you're looking at a bright, uniform light bulb through a frosted window. If there's a particularly thick smudge on the glass, the light behind it will appear dimmer. This is the premise of the supervoid hypothesis. Could a vast, underdense region of space, a cosmic void of staggering proportions, be sitting between us and the CMB, acting like a lens that subtly cools the background radiation? This process is known as the integrated Sachs-Wolf effect. As light travels through such a void, it must climb out of a gravitational well that is actually becoming shallower over time due to the influence of dark energy. This loss of gravitational potential energy manifests as a slight net redshift of the photons, making them appear cooler. It's a well-understood physical effect. The problem is the scale. To produce the observed cooling, this void would need to be truly monstrous, perhaps 1 billion light-years across and profoundly empty. While we have mapped large voids in the cosmic web, nothing of this immense size and emptiness has ever been conclusively found. Surveys of galaxies in the direction of the cold spot have found some under dense regions, but they appear too small and not nearly empty enough to account for the massive temperature drop. The supervoid explanation, while physically sound, requires a void of such extreme proportions that it would itself be a major cosmic mystery. If a simple, albeit gigantic, hole in space can't fully explain it, then we must turn to more exotic ideas. One of the most fascinating possibilities involves a defect in the very fabric of spacetime itself, a relic from a phase transition in the universe's earliest moments. Theorists call this concept a cosmic texture. In the first fractions of a second after the Big Bang, the fundamental forces of nature are believed to have undergone spontaneous symmetry breaking, separating from a unified superforce into the distinct forces we know today. Much like cracks forming in ice as water freezes, these transitions could have created topological defects in the structure of the universe's cosmic strings, domain walls, or textures. A texture is a knot-like defect in the quantum fields that fill the universe. If such a texture existed and then unwound or collapsed, it would create a powerful gravitational potential well. Photons from the CMB passing through this region would lose energy climbing out of this well, resulting in a cold spot exactly like the one we observe. This explanation is incredibly compelling because it ties the anomaly directly to physics at the highest energy scales, offering a potential window into the unification of forces. If true, the cold spot would be the first empirical evidence for such an exotic cosmic defect. Then there is the most mind-bending hypothesis of all, the possibility that the cold spot is evidence of a collision with another universe. This idea springs from the theory of eternal inflation and the multiverse. In this view, our universe is just one expanding bubble in a foaming multiverse of other bubble universes. If another bubble universe collided with ours in the distant past, the immense energy released at the boundary of that collision could have imprinted a specific signature on the CMB of our universe. That signature, according to some calculations, would be a circular, anisotropic cold spot. The appeal of this idea is its sheer audacity. It suggests we might have observational evidence for realities beyond our own. The challenge, of course, is that it pushes the boundaries of testable science. How do you prove you've detected another universe? The theory makes specific predictions about the polarization patterns of the light within the cold spot, offering a potential way to distinguish it from other explanations, but conclusive data remains elusive. The enduring mystery of the CMB cold spot lies in this tension between the mundane and the magnificent. Is it a statistical fluke, a cosmic roll of the dice that just happened to land on a very unlikely number? Is it a supervoid challenging our understanding of how structure forms on the largest scales? Or is it something far more profound, a fossil from the birth of the cosmos, or even a bruise from a collision with a parallel reality? Each possibility forces us to confront the limits of our knowledge. The cold spot is a ghost in the machine of our cosmological models, a persistent anomaly that refuses to be ignored. It serves as a powerful reminder that our map of the universe is still incomplete, and that the most distant light we can see may still hold secrets capable of rewriting our cosmic story. While the Kuiper cliff hints at a void sculpted by an unseen hand, the evidence for a hidden giant doesn't end there. The gravitational plot thickens significantly when we examine the bizarre orbital ballet of the most distant objects in our solar system, a celestial dance that points to one of the most compelling modern astronomical detective stories, the hunt for Planet 9. This search began not with a direct observation, but with a pattern so peculiar it couldn't be ignored. Astronomers studying the orbits of extreme trans-Neptunian objects, icy worlds like Sedna that swing hundreds of astronomical units from the Sun, noticed something deeply strange. These orbits weren't randomly oriented. Instead, their closest approaches to the Sun, their perihelia, were clustered together in space. Even more tellingly, their orbits were tilted in a similar way, all shepherded into a configuration that should be statistically impossible if Neptune were the only major gravitational influence out there. It was as if an invisible conductor was guiding these distant ice dwarfs, keeping them in a synchronized, clustered formation against the natural chaotic rhythm of the solar system. The most plausible explanation for this orchestration is the gravitational pull of a massive, undiscovered planet. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown published a detailed mathematical model that made a stunning prediction. To account for the observed orbital clustering, a planet must exist with a mass roughly 5 to 10 times that of Earth. Its orbit would be colossal and elliptical, taking it from a perihelion of around 200 astronomical units to an aphelion perhaps 700 or even 1200 astronomical units away. A single year on this world would last an astonishing 10 to 20,000 Earth years. This isn't a mere dwarf planet. This is a bona fide super-Earth or mini-Neptune, a class of planet we commonly find around other stars but never expected to be lurking undetected in our own cosmic backyard. Finding this ghost planet, however, is a monumental challenge that explains why it has remained hidden for so long. At its predicted distance, even a giant world would receive virtually no sunlight, making it incredibly faint. We wouldn't be looking for a bright pinprick of light, but for an object hundreds of thousands of times fainter than Pluto. Compounding the difficulty is the sheer vastness of the search area. The possible orbit is a huge, elongated ellipse sweeping through a massive volume of space. It's the ultimate needle in a haystack problem, where the haystack is the size of a continent and the needle is a speck of coal on a moonless night. Yet the search is on, utilizing some of the most powerful telescopes on Earth. Projects like the Subaru telescope's hypersensitive hyper-subprime cam are systematically scanning the predicted swaths of sky, taking images weeks or months apart and looking for the faintest star that moves ever so slightly against the fixed background. Each potential candidate requires painstaking follow-up to confirm its orbit, a process of elimination that has so far ruled out large portions of the hypothetical planet's predicted path. The hunt is slow and methodical, a testament to both the ingenuity of astronomers and the profound difficulty of seeing the darkest corners of our own solar system. The implications of discovering Planet 9 would be nothing short of revolutionary. Its mere existence would force a complete rewrite of solar system formation models. How did a planet 5 times more massive than Earth end on such a distant, eccentric orbit? The leading theory suggests it may not have formed out there at all. It could be an exiled giant, a core that formed alongside Jupiter and Saturn only to be violently ejected outward by a gravitational tug of war with its larger siblings in the solar system's chaotic youth. Its discovery would provide a stunning missing chapter in our own cosmic history, a fossilized record of the dynamic instability that shaped the planetary system we see today. Furthermore, its gravitational influence might explain other solar system anomalies, such as the unusual tilt of the Sun's axis, providing a unified solution to several mysteries at once. The quest for Planet 9 is more than just a search for another world. It is a direct test of our understanding of how planetary systems are born and evolve, and whether our own home is stranger and more wonderful than we ever imagined. So how do we bridge this gap between the universe's baby pictures and its current state? Astronomers have turned to a completely new and independent cosmic siren, gravitational waves. When two ultra-dense objects like neutron stars spiral into each other and merge, they create ripples in the fabric of space-time itself. The beauty of these events is that the amplitude of these gravitational waves tells us exactly how much energy was released in the collision, which in turn reveals the intrinsic luminosity of the event. This makes them standard sirens. We can measure the strength of the signal to directly calculate the distance to the source without needing any of the traditional cosmic distance ladder rungs. In 2017, the historic detection of the neutron star merger known as GW170817 provided the first such measurement. By combining the gravitational wave distance with the redshift of the host galaxy, scientists could calculate the Hubble constant directly. The result fascinatingly leaned towards the higher local universe value, adding a powerful new data point that seems to side with the Cepheids and supernova. This suggests the tension isn't an artifact of one measurement technique, but a real, physical discrepancy that appears no matter how we choose to measure the modern expansion. This convergence of evidence from independent methods makes the case for new physics increasingly compelling. If the error were simply in our measurement of the cosmic distance ladder, the gravitational wave standard sirens would likely have revealed a different answer. The fact that they seem to corroborate the faster expansion rate forces us to look beyond mere observational mistakes and consider that our standard model of cosmology, known as lambda cold dark matter, might be missing a crucial ingredient. This model has been incredibly successful at describing the large-scale structure of the universe, but the Hubble tension is its most significant failure. Cosmologists are now exploring a zoo of exotic possibilities to resolve this crisis. One leading idea is the concept of early dark energy. This proposes that a temporary form of dark energy existed in the universe's first few 100,000 years, a transient field that added an extra push to the expansion during the epoch of Big Bang nucleosynthesis and the release of the cosmic microwave background. This extra burst of acceleration would have subtly altered the conditions imprinted on the CMB, meaning that when we use the CMB to predict today's expansion rate, we get a slower value. Meanwhile, the local measurements of the modern era would be unaffected, perfectly creating the divide we observe. It's as if the universe had a growth spurt in its infancy that we hadn't previously accounted for. Other theories are even more radical, suggesting modifications to Einstein's theory of gravity itself on the largest cosmic scales. Perhaps gravity behaves slightly differently over immense distances than our equations predict, causing the expansion to accelerate faster in the modern era than our models allow. There are also proposals involving new types of neutrinos or other exotic relativistic particles that could have influenced the early universe's expansion history. The challenge with all these ideas is that they must not only solve the Hubble tension, but also remain consistent with the vast array of other successful predictions made by the Standard Model. A proposed tweak to fix one problem cannot break everything else we know about cosmology. This makes the hunt for a solution a delicate and thrilling balancing act. The resolution to this tension promises to be far more than a simple calibration fix. It is a potential gateway to a deeper layer of physical reality, hinting that our understanding of the cosmos, for all its sophistication, is still only a glimpse of a much richer and more complex truth. And now we arrive at perhaps the most profound and deeply personal mystery on our list, one that doesn't just question the nature of the cosmos, but the very nature of reality and our role in shaping it. This is the quantum measurement problem, and it begins with a simple, childlike question: what happens when you're not looking? In the bizarre world of quantum mechanics, particles don't have definite properties until we measure them. An electron isn't here or there. It exists in a blurry cloud of probability, a superposition of all possible locations at once. It spins in all directions simultaneously. This isn't a lack of knowledge. It's the fundamental state of being for a quantum object, perfectly described by its wave function. The puzzle, the true heart of the mystery, is what happens the moment we decide to look. The act of measurement seems to force the electron to make a choice. The spread-out wave function in an instant collapses into a single, definite point. The myriad possibilities vanish, and a single reality clicks into place. But why? What is so special about a measurement? When exactly does this collapse occur, and what in the universe has the power to cause it? This seemingly simple question has tortured physicists for nearly a century, because the mathematics of quantum mechanics describes the bizarre superposition state perfectly, but it says absolutely nothing about how or why it collapses upon observation. This has led to a spectrum of interpretations, each more mind-bending than the last, because they are not just about physics, they are about philosophy and the very meaning of existence. The most traditional view is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. In this view, the wave function collapse is a fundamental, irreversible process. The quantum world is inherently probabilistic, and it is the act of observation by a classical measuring apparatus, be it a Geiger counter or a human eye, that forces a definite outcome. But this immediately raises the infamous Wigner's friend paradox. Imagine a physicist in an isolated lab measures a quantum particle and sees a specific result. To her, the wave function has collapsed, but to you, outside the lab, the entire system. The physicist, the lab, and the particle is still in a superposition until you open the door and ask for the result. So whose observation counts? This interpretation uncomfortably places consciousness itself at the center of the process, suggesting that reality is not independent of the mind that perceives it, a notion that many scientists find deeply unsatisfying. In stark opposition stands the many worlds interpretation proposed by Hugh Everett. This is a breathtakingly bold solution that does away with collapse entirely. Everett said the wave function never collapses. Instead, at the moment of measurement, the universe itself splits into multiple, non-communicating branches. In one universe, you see the electron spin up. In another, an identical version of you sees it spin down. Every quantum decision point creates a new, parallel reality, meaning there's a universe where every possible outcome of every quantum event actually occurs. The appeal here is that it removes the need for a special observer. The mathematics just chugs along, and reality becomes a vast, ever-branching tree of possibilities. The cost, however, is an almost incomprehensible proliferation of universes, a multiverse of staggering proportions where countless versions of ourselves live out every conceivable existence. Other interpretations try to find a middle ground. Objective collapse theories propose that wave-function collapse is a real physical process, but it isn't triggered by consciousness. Instead, it happens spontaneously when a quantum system becomes too large or too complex, perhaps due to a tiny, never-before-detected field or a gravitational effect. This would draw an objective, physical line between the quantum and classical worlds. Then there is the pilot wave theory, a modern revival of a deterministic idea from Louis de Broglie. In this view, particles are real and have definite positions at all times, but they are guided by a mysterious pilot wave that dictates their motion. The strange probabilistic nature of quantum mechanics arises from our ignorance of the exact initial conditions of this wave, not from any fundamental fuzziness in reality itself. This interpretation is compellingly intuitive but comes with its own baggage, including requiring that influences can travel faster than light in a way that doesn't allow for communication, preserving the weirdness while trying to restore a concrete reality. The implications of solving the measurement problem are almost beyond calculation. It strikes at the core of what we mean by reality, information, and even free will. If the Copenhagen interpretation is correct, then consciousness is not an emergent property of the brain, but a fundamental component of the universe. If many worlds is true, then our sense of a single, linear history is the ultimate illusion, and our individual lives are just one thread in an infinite tapestry. This isn't just abstract philosophy. The quest to understand the quantum to classical transition is driving real-world experiments. Scientists are now pushing the boundaries of quantum superposition, trying to put larger and larger objects, clusters of atoms, then viruses, then tiny mechanical oscillators, into a superposition state to see just how big something can get before it is forced to behave classically. Each experiment is a probe into the unknown, testing the limits of our interpretations and pushing us closer to an answer. The quantum measurement problem remains the grand, unresolved chord at the heart of modern physics, a silent question hanging in the air every time we open our eyes and expect the world to be there, solid and waiting. But if the quantum measurement problem challenges our understanding of reality on the smallest scales, our next cosmic mystery pushes our physical laws to their absolute breaking point on the grandest of scales, at the very heart of the universe's most terrifying and enigmatic objects. We've journeyed through the event horizon and pondered the information paradox, but now we must confront the ultimate destination of that inward fall, the black hole singularity. According to Einstein's theory of general relativity, the inward crush of a black hole's gravity doesn't stop at the event horizon. Once matter crosses that point of no return, there is no force in the universe powerful enough to halt its descent. All of that material, stars, gas, planets, even light itself, is doomed to be crushed into an infinitely small point at the very center. This is the singularity, a region where the density becomes infinite, the curvature of space-time becomes infinite, and all the known laws of physics simply cease to function. It's a place where time, as we understand it, effectively comes to an end. General relativity, our most powerful theory of gravity, predicts its own demise at this point, yielding a result that is mathematically nonsensical and physically impossible. An infinity in a physical theory is nature's way of telling us we're missing a crucial piece of the puzzle. The problem is that general relativity is a classical theory. It doesn't incorporate the weird, fuzzy rules of the quantum world that govern the behavior of matter on the smallest scales. But a singularity involves packing an enormous amount of mass into a volume smaller than a single atom, a realm where quantum effects must be dominant. This means that to truly understand what happens at the center of a black hole, we cannot rely on gravity alone. We need a theory that successfully merges general relativity with quantum mechanics. We need a theory of quantum gravity. This is the holy grail of modern physics, and the black hole singularity is its most stringent and dramatic test. Several major approaches are vying to solve this profound mystery. String theory, perhaps the most famous candidate, proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. Different vibrations of these strings correspond to different particles and forces. In this framework, the terrifying mathematical infinity of the singularity might be replaced by a tangle of these ultra-small strings, a sort of fuzzball that has a finite, albeit still extreme, size and density. This could resolve the paradox by eliminating the infinitely dense point entirely, suggesting that matter simply cannot be compressed beyond a certain fundamental scale dictated by the strings themselves. A competing and radically different approach is loop quantum gravity. This theory proposes that spacetime itself is not a smooth, continuous fabric, but is instead woven from a network of tiny, discrete loops, a kind of atomic structure of space and time. This granularity provides a natural limit to how much reality can be squeezed. In this view, the crushing gravity of a black hole's core doesn't create an infinite point, but instead meets a sort of quantum resistance from this fundamental spacetime fabric. The matter rebounds from this ultra-dense state, potentially transforming the black hole's singularity into a bridge to another region of spacetime, a concept that aligns with the theoretical idea of a white hole or even a gateway to another universe. This quantum bounce offers a stunning alternative to the bleak, infinite death predicted by classical physics. There are other, even more speculative ideas. Some models suggest that within the singularity, the very dimensions of spacetime get tangled up, with space behaving like time and time behaving like space, fundamentally altering the nature of causality and preventing the formation of a true infinity. The challenge with all of these theories is that they are currently nearly impossible to test directly. We cannot peer inside a black hole, and creating quantum gravitational effects in a laboratory is far beyond our current technology. Yet the pursuit is far from futile. Understanding the singularity isn't just about solving a mathematical curiosity. It's about uncovering the fundamental nature of reality. The laws that govern the center of a black hole are the same laws that govern the entire universe during the first moment of the Big Bang, which was itself a singularity. By deciphering the physics of how a singularity truly works, we are effectively learning the rules for the birth of the cosmos. The black hole is a natural laboratory, forcing matter into states of energy and density that we can never recreate on Earth, offering us a unique window into the deepest laws that weave the fabric of spacetime itself. The quest to solve the singularity is the quest to complete the picture of our universe, from its violent beginning to its most mysterious endpoints. For all the mysteries we've explored, from quantum foam to cosmic voids, they all lead to one final, overwhelming question: how does it all end? The destiny of the entire universe hinges on a cosmic tug-of-war between two invisible adversaries: gravity, which pulls everything together, and dark energy, which pushes everything apart. Right now, the evidence is clear: dark energy is winning, and its exact nature will write the final chapter for all of existence. The most widely accepted forecast based on our current measurements is known as the Big Freeze or heat death. In this scenario, dark energy continues to accelerate the expansion of the universe at its current rate. Distant galaxies will first be pushed away so fast that their light can no longer reach us, leaving the observable universe an increasingly dark and lonely place, containing only our gravitationally bound local group. Then, within these isolated islands, the machinery of creation will grind to a halt. All the interstellar gas needed to form new stars will be locked away in aging stellar remnants, and one by one, the stars themselves will burn out. Black holes will slowly evaporate over trillions of years via Hawking radiation, their final moments punctuating the darkness with a faint pop. Eventually, the universe will approach a state of absolute zero temperature, a vast, silent, and utterly uniform graveyard where no energy can be transferred, no work can be done, and no new event of any significance will ever occur again. It is not a violent end, but a quiet, eternal fading of all light and life. But what if dark energy isn't a constant force? What if it grows stronger over time? This possibility leads to a far more dramatic and terrifying finale, the Big Rip. If the repulsive force of dark energy were to intensify, eventually overcoming even the strongest local bonds holding matter together, the expansion would not just accelerate galaxies away from each other, it would tear apart the very fabric of reality itself. First, galaxy clusters would be shredded, then individual galaxies. With the expansion force now overwhelming gravity, solar systems would be pulled apart. Planets would be ripped from their stars. In the final moments, the force would exceed the strength of atomic bonds, dismantling every molecule, every atom, and even the nuclei of atoms themselves. The universe would end not with a whimper, but with a catastrophic, instantaneous unraveling of space-time into a chaotic sea of disconnected fundamental particles. Yet another deeply unsettling possibility emerges not from cosmology, but from quantum field theory, vacuum decay. This theory suggests that the Higgs field, which gives particles their mass, might not be in its true, most stable state. Think of our universe as existing in a valley, but there might be a much deeper valley, a true vacuum with lower energy. A random quantum fluctuation could create a tiny bubble of this true vacuum somewhere in the universe. This bubble would then expand in all directions at the speed of light, rewriting the laws of physics as it goes. The fundamental constants we rely on, the mass of an electron, the strength of gravity, would change instantly. Atoms would cease to hold together, and chemistry as we know it would become impossible. The wave of destruction would be completely undetectable until it arrived, as no signal can outrun it. One moment the universe would exist, the next it would be transformed into something completely alien and almost certainly uninhabitable. Amidst these bleak conclusions, other theories offer a spark of renewal. The concept of a cyclical universe suggests that the cosmos might have no true beginning or end, but instead undergoes an endless series of expansions and contractions, a perpetual cycle of big bangs and big crunches. In some models, the universe expands to a maximum size before dark energy dissipates and gravity pulls everything back into a singularity, which then rebounds in a new Big Bang. Another version, conformal cyclic cosmology, proposes that an infinitely expanding, empty universe can be mathematically transformed into the high-energy singularity of a new Big Bang, meaning the end of one eon becomes the beginning of the next. These ideas offer a poetic alternative to eternal silence, suggesting that death is always followed by rebirth on a cosmic scale. Ultimately, the greatest challenge in predicting our fate is that the answer depends on physics we have not yet mastered. Is dark energy truly constant? Will it weaken, strengthen, or even change sign? The properties of this mysterious force are the single biggest variable in the equation. Our ability to peer into the deep future is limited by our understanding of the deep present. Each new telescope, each more precise measurement of the universe's expansion, brings us closer to knowing which destiny is ours. The quest to answer this ultimate question forces us to confront not just the nature of the cosmos, but the meaning of our own fleeting existence within it. In searching for the end, we are ultimately trying to understand the complete story of which we are a part, a story whose final paragraph remains the greatest unsolved mystery of all. From the invisible grip of dark matter binding galaxies together to the repulsive push of dark energy tearing the cosmos apart, we've journeyed through a universe brimming with enigmas. We've stood at the edge of a black hole singularity where physics itself breaks down and pondered the spooky connection of quantum particles that challenges our very notion of reality. We've followed elusive signals like the WOW burst and marveled at interstellar visitors like Oumuamua, each a tantalizing piece of a puzzle we are only beginning to assemble. These 30 mysteries are not a record of what science has failed to do, but a breathtaking map of everything it has yet to explore. Each one is a beacon guiding us toward a deeper and more profound understanding of existence. They remind us that the universe is not a problem to be solved, but an infinite, unfolding story to be discovered. The greatest achievements in astronomy and physics likely lie not in our past, but in our future, waiting for the next generation of curious minds to build better telescopes, devise grander experiments, and ask even more daring questions. The search for answers is a collective human endeavor, and it's one you can be a part of by simply staying curious. Follow the ongoing work of observatories like the Vera Rubin and James Webb Space Telescopes as they probe these very questions. The next great discovery could be announced tomorrow. So we'd love to hear from you which of these cosmic phenomena captures your imagination the most. Is it the haunting silence of the Fermi Paradox, the bizarre acceleration of Pioneer, or the terrifying potential of a Big Rip? Let us know your thoughts in the comments below, and as always, thanks for joining us on this journey through the great unknown.